Picture standing on the surface of a planet so scorching that metal would boil away like water in a kettle. A world where the very air you breathe would ignite in an instant. This isn't science fiction, it's the reality of Kelt 9b, the hottest known exoplanet, where temperatures soar above 4,300 degrees Celsius. That's hotter than some stars, and yet this is just one extreme in a universe that thrives on pushing the limits of heat and cold beyond anything we can fathom. From the icy void of deep space where temperatures hover just above absolute zero, to the heart of a supernova where matter is torn apart at millions of degrees, the cosmos is a place of unimaginable contrast. What makes these extremes so fascinating isn't just the numbers, it's the sheer defiance of what we consider possible. Imagine a place so cold that atoms nearly stop moving entirely, where time itself seems to slow down. Now flip that image and think of a stellar explosion so violent that it births elements like gold and uranium in a heartbeat. These aren't just abstract ideas, they're the forces that shape galaxies, forge new worlds, and even dictate whether life can exist at all. And today, we're diving into 50 mind-blowing facts about these cosmic temperature extremes, each one a testament to the universe's endless capacity to astonish. This journey isn't just about big numbers or distant phenomena. It's about understanding how these extremes touch everything from the atoms in your body to the fate of the cosmos itself. The same heat that powers stars also forged the iron in your blood. The same cold that chills the void between galaxies could one day freeze the universe into darkness. By the time we're done, you'll see the universe in a whole new light, not just as a collection of distant wonders, but as a living, breathing system where temperature dictates the rules of existence. So buckle up, we're about to explore the hottest, coldest, and most unexpected corners of space, where the laws of physics are pushed to their breaking point and beyond. Imagine a temperature so cold that it doesn't just freeze water, it freezes reality itself. Absolute zero, the theoretical floor of coldness at negative 273.15 degrees Celsius, is where atoms surrender to stillness. At this impossible chill, the frantic dance of particles grinds to a near halt, and the very concept of heat loses meaning. Scientists have come breathtakingly close to this limit, like the Massachusetts Institute of Technology team, who cooled sodium gas to within 0.5 billionth of a degree above absolute zero, creating a bizarre quantum state where atoms lose their individuality and behave like a single wave. Yet true absolute zero remains forever out of reach, and the reason reveals one of the universe's deepest secrets. Even in the emptiest void, quantum mechanics ensures space thrums with energy. These tiny vibrations, known as zero-point energy, mean particles can never fully stop jittering. Nature refuses to let anything sit perfectly still. It's as if the cosmos itself has a minimum volume setting, whispering to atoms, "You may slow down, but you'll never fully rest." The pursuit of these extreme lows isn't just about breaking records. Near absolute zero experiments have unveiled surreal phenomena like superfluids that flow without friction and superconductors that carry electricity with zero resistance. These aren't laboratory curiosities, they could revolutionize technology, from lossless power grids to quantum computers that harness these ultra-cold states to perform calculations impossible for ordinary machines. What makes absolute zero so mesmerizing isn't just the physics, it's the philosophical punch. This temperature represents more than a number. It's the boundary where our classical understanding of reality crumbles, giving way to the strange rules of quantum existence. A realm where certainty dissolves, where particles exist in multiple places at once, and where the very act of observation changes what's being observed. Absolute zero isn't just cold, it's cosmic poetry written in the language of motionless atoms. If absolute zero is the universe's ultimate cold limit, then the Boomerang Nebula is nature's closest attempt to reach it. Located 5,000 light-years away in the constellation Centaurus, this eerie cosmic cloud holds the record as the coldest known natural place in existence, chilling at just 1 degree above absolute zero. That's colder than the background glow of the Big Bang itself. What makes this interstellar deep freezer even more striking is its shape, twin lobes of frigid gas stretching outward like a ghostly bow tie, giving it the illusion of a boomerang caught mid-flight. This nebula wasn't always an icy wonder. It began as a sun-like star entering its death throes, shedding layers of gas in slow, dense winds. But here's where the cosmic refrigeration kicks in. As the dying star's core shrank, it revved up these winds to staggering speeds over 160,000 kilometers per hour. That's like a hurricane blasting outward at 100 times faster than Earth's fastest jet streams. When gas expands that rapidly, it cools dramatically, the same way spraying deodorant from a can feels cold on your skin. The Boomerang Nebula took this principle to an extreme, turning itself into a natural cryogenic machine where molecules slow to a crawl. Scientists suspect its ultra-cold temperatures also come from an invisible partner, a second star orbiting the dying one. As the companion star dances through the expanding gas, it might act like a cosmic spoon stirring a chilled soup, helping spread the cold even farther into space. The result, a nebula so cold that it absorbs heat from the universe around it. Even the feeble warmth of interstellar space, just 3 degrees above absolute zero, is too much for this frosty giant. It's literally siphoning thermal energy from its surroundings, defying the usual rules where objects eventually reach equilibrium with their environment. The Boomerang Nebula isn't just a curiosity, it's a preview of our own sun's distant future. In about 5 billion years, our star too will shed its outer layers, potentially creating a similar icy spectacle. But there's a key difference. Our solar system lacks a binary companion to supercharge the cooling process. That means Earth's future nebula may never get quite as cold as this record-breaking cosmic freezer. Still, studying the boomerang gives astronomers a blueprint for how stars transform into these intricate icy structures, proving once again that the universe's most extreme places often hold the keys to understanding our own origins. Pluto may no longer be called a planet, but it still holds cosmic records, like being home to some of the most bone-chilling landscapes in our solar system. At negative 233 degrees Celsius, its surface is colder than most objects in the Kuiper belt, a region filled with icy bodies drifting beyond Neptune. What keeps Pluto in this deep freeze? The answer lies in its delicate blanket of nitrogen ice, a frost so volatile that it sublimates, transforming directly from solid to gas under even the faint warmth of the distant sun. When NASA New Horizons spacecraft raced past Pluto in 2015, it captured jaw-dropping images of terrain wrinkled like snakeskin, a testament to the dwarf planet's violent temperature swings. These bizarre ridges, some as tall as skyscrapers, form as Pluto's surface contracts like a deflating balloon. Over millions of years, its nitrogen ice cools and cracks, fracturing into jagged patterns that defy earthly geology. Unlike water ice, which shatters cleanly, nitrogen behaves more like taffy when frozen, stretching and snapping under pressure to create those otherworldly textures. But Pluto's cold isn't uniform, it's a patchwork of extremes. The heart-shaped Tombaugh Regio, a vast plain of nitrogen ice, acts like a natural refrigerator, its gleaming surface reflecting sunlight and locking in the chill. Meanwhile, darker regions coated in organic compounds absorb just enough solar radiation to create minuscule but vital thermal variations. These subtle differences drive winds in Pluto's whisper-thin atmosphere, pushing nitrogen vapor from warmer zones to colder ones in a slow-motion weather cycle that reshapes the landscape seasonally. What's truly astonishing is how active Pluto remains despite its frigid state. Glaciers of nitrogen creep across its valleys, ice volcanoes may erupt with frozen slush, and entire mountain ranges float atop denser water ice like cosmic icebergs. This isn't a dead world, it's a dynamic one where cold isn't just an absence of heat but an architect of alien geology. Pluto's extreme chill challenges our assumptions about what habitable might mean, proving that even in the darkest, coldest corners of the solar system, nature finds ways to surprise us. Beneath the rust-colored streaks crisscrossing Europa's icy shell lies one of the solar system's most tantalizing paradoxes, a surface colder than a winter night in Antarctica, yet possibly hiding an ocean warmer than Earth's tropics. At -220 degrees Celsius, Jupiter's enigmatic moon wears a frozen crust thicker than Mount Everest is tall, a glittering armor against the vacuum of space. But peer deeper, and this world reveals its secret. Tidal forces from Jupiter's immense gravity squeeze and stretch Europa like a cosmic stress ball, generating enough heat to maintain a liquid water ocean beneath the ice. The cracks scarring Europa's surface tell the story of this hidden warmth. These fractures aren't static, they're dynamic highways for energy, with some plumes shooting water vapor over 100 kilometers into space. Imagine geysers so powerful they could dwarf Old Faithful, fueled not by volcanic heat but by the flexing of the moon itself. Every time Europa orbits Jupiter, the gas giant's gravitational pull warps the moon's interior, creating friction that melts ice from below. This process turns the subsurface into a churning, salty sea possibly twice the volume of Earth's oceans, sealed under an icy ceiling. What makes Europa's cold shell so fascinating is how it acts as both a barrier and a messenger. The ice isn't just a lifeless lid, it's a canvas recording clues about what lies beneath. Dark streaks along fractures might be deposits of sea salt or organic compounds dragged upward from the ocean. Patterns in the terrain suggest the ice shifts like tectonic plates, with warmer blobs slowly rising while colder sections sink. Even the temperature variations across the surface hint at hotspots where warmth briefly breaches the frosty exterior before freezing solid again. Scientists suspect these bursts of heat could create temporary pockets of slushy brine within the ice itself, microenvironments where life might cling, similar to Earth's Antarctic subglacial lakes. Future missions like NASA Europa Clipper aim to map these thermal leaks, searching for chemical signatures that would confirm the ocean's habitability. It's a reminder that cold isn't always sterile. Sometimes it's the protective layer shielding a world teeming with possibilities. Europa's frozen face challenges us to rethink where life could thrive, not despite the cold, but because of the delicate balance it maintains between ice and fire. While Mars basks in its nickname as the Red Planet, its polar winters paint a far frostier picture, one where temperatures plunge to -153 degrees Celsius, turning the thin air into a swirling nightmare of carbon dioxide snow. Unlike Earth's snowy landscapes shaped by water ice, Mars' poles endure blizzards of frozen CO2, where flakes the size of red blood cells drift through skies too thin to even feel like a true storm. This isn't the fluffy snowfall we know. It's a ghostly precipitation, almost invisible, accumulating so slowly that a human observer might mistake it for fog. The root of this deep freeze lies in Mars' wispy atmosphere, just 1% as dense as Earth's. With barely any air to trap heat, warmth vanishes into space almost instantly when the sun dips below the horizon for months-long polar nights. To put that in perspective, Earth's coldest recorded temperature, -89 degrees Celsius in Antarctica, would feel practically balmy compared to Mars' pole. And while our planet's icy extremes are softened by oceans and thick atmosphere acting like thermal blankets, Mars has no such refuge. Its surface cools like a stone left in a freezer, radiating heat away until even the carbon dioxide in its air freezes solid. Yet this extreme cold isn't just a curiosity, it reshapes the planet. During winter, up to 30% of Mars' already scant atmosphere condenses into frost, draping the poles in eerie dry ice caps. These seasonal deposits are so vast they alter the planet's atmospheric pressure globally, creating ripples in weather patterns felt even at the equator. When spring finally returns, the CO2 doesn't melt. It sublimates back into gas, triggering winds so fierce they spiral into continent-sized dust storms. What's most striking is how these frigid tempests mirror Earth's own climate machinery, just stripped down to brutal simplicity. Mars shows us a world where cold isn't moderated by oceans or greenery, where thermodynamics runs unchecked. It's a laboratory for understanding how thin the line is between a habitable world and a frozen desert, and a reminder that even in the harshest cold, planetary forces never stop moving. Tucked away in the Moon's polar craters, where sunlight never reaches, lies a cold so intense it makes Pluto's winters seem mild, -247 degrees Celsius, the chilliest temperatures ever recorded in our solar system. These permanently shadowed regions are like nature's deepest freezers, with walls so steep and locations so perfectly aligned that not a single photon of sunlight has touched their floors in billions of years. The cold here isn't just extreme, it's eternal. What makes these lunar shadows even more fascinating is what they've been silently collecting: water ice. Over millennia, comets and asteroids delivering water molecules to the Moon's surface saw them bounce like microscopic pinballs until they rolled into these icy death traps. Once there, the relentless cold locked them in place, preserving them like cosmic time capsules. NASA, a lunar reconnaissance orbiter, has mapped these craters in stunning detail, revealing glittering patches where ice concentration is so high it could fill thousands of Olympic swimming pools. But how does ice survive on an airless world where daytime temperatures can boil water? The answer lies in the Moon's lack of atmosphere. Without air to transfer heat, the shadowed craters exist in a state of perfect insulation. The surrounding sunlit terrain might sizzle at 120 degrees Celsius, but just a few meters away, inside the crater's umbra, the cold is so absolute that molecules stop vibrating. It's like opening a freezer door in a scorching desert. The heat never penetrates the darkness. These cold traps aren't just scientific curiosities, they're potential treasure troves for future explorers. Water ice isn't just crucial for drinking. It can be split into hydrogen and oxygen for rocket fuel or life support, turning the Moon into a cosmic gas station. Private companies and space agencies are already racing to land probes in these regions, hoping to drill into the ice and unlock its secrets. The coldest places on the Moon might just become the hottest real estate in the solar system. Yet studying these craters comes with bizarre challenges. Landing a spacecraft in perpetual darkness means relying on battery-powered heaters to keep electronics from freezing solid within minutes. Even a rover's tracks could disturb the fragile ice, causing it to vaporize instantly in the vacuum. It's a delicate dance of engineering and physics, where one wrong move could erase the very resources we're trying to harvest. The Moon's shadowed craters force us to rethink what extreme really means. They're not just cold, they're time machines, preserving primordial water from the solar system's infancy. They're vaults safeguarding the building blocks of life in a darkness so complete it defies imagination. And as we prepare to return to the Moon, these freezing abysses may hold the key to unlocking humanity's future among the stars. Titan, Saturn's largest moon, is a world where the impossible becomes routine, where rivers carve valleys through ice as hard as rock, and lakes stretch wider than the Great Lakes of North America, yet they're filled not with water but with liquid methane, chilling at -179 degrees Celsius. This isn't just cold, it's a parallel Earth, a looking-glass version of our hydrologic cycle, but with methane playing the role of water. When the European Space Agency's Huygens probe touched down on Titan in 2005, it sent back images of rounded pebbles littering a dry riverbed, stones smoothed not by rushing water but by flowing hydrocarbons, proof of an active alien erosion process unfolding in ultra-slow motion. The scale of Titan's methane seas defies earthly comparison. Kraken Mare, the largest known body, sprawls over 400,000 square kilometers larger than the Caspian Sea, with depths exceeding 300 meters. But here's the twist: this isn't pure methane. Radar data from NASA Cassini spacecraft revealed these lakes are chemical cocktails, blending methane, ethane, and dissolved nitrogen like some surreal cryogenic cocktail. When waves form slowed by Titan's thick atmosphere and low gravity, they ripple at just a fraction of the speed of Earth's ocean waves, creating a sluggish, almost dreamlike motion. What makes Titan's cold so extraordinary is how it reinvents familiar processes. Rain falls here, but it's methane drizzle, droplets forming at altitudes 50 kilometers high and taking hours to reach the surface. Evaporation happens, but so slowly that a puddle might take centuries to vanish. Even the shoreline erosion is bizarre water ice, normally brittle as glass at these temperatures, becomes slightly malleable under Titan's conditions, allowing methane waves to sculpt it into cliffs and bays over geologic time. The Huygens probe's landing site showed clear evidence of this, channels branching like fractal veins across the landscape, carved by downpours that might occur only once every few Titan years, equivalent to 30 Earth years. Yet Titan's frigid lakes aren't just geologic oddities, they're laboratories for probiotic chemistry. The constant cycling of hydrocarbons between liquid and gas could be driving reactions similar to those that sparked life on Earth, just at temperatures cold enough to freeze oxygen solid. Some scientists speculate that Titan's subsurface ocean, locked beneath its icy shell, might even host life adapted to liquid methane instead of water, a concept that reshapes our very definition of habitability. The haunting beauty of Titan's cryogenic seas lies in their contradictions. They're frozen in time yet constantly evolving, utterly alien yet eerily familiar. They challenge us to expand our understanding of how worlds work, proving that even in the deepest cold, nature finds ways to mimic the rhythms of home. Uranus spins on its side like a cosmic bowling ball knocked over by some celestial strike, a peculiarity that makes it the solar system's ultimate icebox. While Neptune, its distant blue sibling, basks in relative warmth at -200 degrees Celsius, Uranus' upper atmosphere plummets to a staggering -224 degrees, nearly matching the chill of Pluto despite being over 1 billion kilometers closer to the Sun. This counterintuitive deep freeze has puzzled scientists for decades, and the answer lies in the planet's bizarre tilt and its refusal to recycle heat like other gas giants. Most planets release internal heat leftover from their formation, but Uranus hoards its energy like a cosmic miser. Unlike Neptune, which radiates 2.6 times more heat than it receives from the Sun, Uranus emits barely a flicker, just 1.1 times the solar energy it absorbs. Some speculate a colossal impact early in its history may have blasted away much of its primordial warmth, leaving its core oddly quiescent. But the real key to its frigid upper layers is that 98-degree axial tilt, which pitches entire hemispheres into darkness for 21-year stretches. Imagine winters where the sun vanishes for a generation, where clouds of methane ice crystallize in endless twilight. While Earth's poles endure months of darkness, Uranus' polar regions spend decades without sunlight, allowing heat to bleed relentlessly into space. The lack of violent storms common on Neptune further prevents warm gas from rising to the upper atmosphere, leaving it isolated in a perpetual chill. Even Uranus' magnetic field, oddly offset from its center, fails to generate enough friction to warm things up significantly, yet this icy enigma might hide secrets beneath its bland exterior. Recent observations reveal fleeting storms and bright methane clouds in its upper layers, hints that some heat does percolate upward, just not enough to break its deep freeze. The James Webb Space Telescope's infrared eyes are now probing these mysteries, seeking to map temperature variations that could explain why Uranus remains the solar system's coldest giant. What makes Uranus cold so compelling isn't just the number, it's the lesson in planetary diversity. Two nearly twin worlds born from the same cosmic nursery, yet one simmers with inner fire while the other languishes in icy stillness. It's a reminder that in the universe, proximity to the sun doesn't always dictate temperature. Sometimes it's the quirks of a planet's past and posture that write its thermal fate. Venus wears two faces, one a blistering hellscape, the other a frozen wasteland, and the difference between them could shatter steel. While its day side bakes at 460 degrees Celsius, hot enough to melt lead, the night side plunges to negative 175 degrees, colder than a Siberian winter. This staggering 235-degree swing isn't just extreme. It's a masterclass in atmospheric betrayal, where the same thick blanket of carbon dioxide that traps heat on the day side abandons the night side to cosmic frost. The Soviet Union's Venera landers, the only probes to survive Venus' crushing atmosphere long enough to measure these extremes, revealed just how capricious this world is. Venera 8, touching down in 1972, recorded nighttime temperatures so low that its instruments initially malfunctioned, unable to process the rapid cool-down. The irony is brutal. A planet with an atmosphere 92 times denser than Earth's, yet so sluggish at redistributing heat that the night side might as well be another world. Sunlight takes 4 months to circulate from day to night, leaving vast regions starved of warmth for Earth-length years. What makes Venus' cold side so eerie is how it defies logic. On Earth, oceans and winds smooth out temperature swings, but Venus' supercritical carbon dioxide, a fluid so dense it behaves like both gas and liquid, moves in sluggish waves, pooling heat near the equator while the poles languish in perpetual chill. High-altitude winds scream at 360 kilometers per hour, yet they're too aloof to share warmth with the surface below. The result, a twilight zone where the ground freezes solid beneath a smothering, sulfur-laced sky. This duality isn't just a curiosity, it's a warning. Venus shows us what happens when a planet's atmosphere turns from regulator to tyrant, where runaway greenhouse effects and thermal inertia create unlivable extremes. As we study exoplanets with thick atmospheres, Venus stands as a cosmic caution sign, a world where temperature isn't just a number, but a prison sentence written in gas and wind. Mercury's chaotic dance with temperature extremes would give any planet whiplash. Dayside surfaces roasting at 430 degrees Celsius, hot enough to liquefy zinc, while shadowy polar craters huddle at negative 193 degrees, colder than Antarctica's deepest ice. This staggering 600-degree split exists because Mercury, lacking any meaningful atmosphere to redistribute heat, becomes a world of absolute opposites. The secret to its icy poles lies in craters so deep and perfectly placed that their floors have dwelled in perpetual darkness for billions of years, untouched by the sun's searing gaze. When NASA Messenger probe mapped these frozen sanctuaries in 2012, its radar instruments detected something astonishing: glittering patches reflecting signals exactly like water ice. These weren't just traces. Some deposits spanned entire crater basins with enough frozen water to bury Washington, D.C., under a layer thicker than the Washington Monument is tall. The ice survives thanks to Mercury's minimal axial tilt, just 2 degrees compared to Earth's 23.5, locking certain craters in eternal shadow. Picture standing at the bottom of these pits. Towering walls block all sunlight, creating a cold trap so efficient that even the faintest heat from the planet's core or the distant stars can't penetrate the freeze. But here's the cosmic irony: these same craters often sit just a few kilometers from plains where temperatures would vaporize a human instantly. It's as if Mercury carved out deliberate refrigerators next to its furnaces. Some of the largest ice deposits cluster around the North Pole's Chaucer crater, where radar revealed layers up to 20 meters thick mixed with dark organic material, possibly delivered by comets that slammed into the planet over eons. These organics act like a thermal blanket, preventing the ice from sublimating even during Mercury's closest approaches to the Sun. The origin of this ice rewrites assumptions about our solar system's history. Unlike Earth's water, which likely arrived via asteroids during the late heavy bombardment, Mercury's ice might have multiple sources: volcanic outgassing from its ancient past, chemical reactions between solar wind hydrogen and surface minerals, and yes, those occasional comet strikes. Messenger data even hinted at patches of frozen carbon dioxide hiding among the water ice, suggesting Mercury's poles could be time capsules preserving chemicals from the solar system's infancy. What makes these freezing vaults so valuable isn't just their existence, it's their accessibility. Future lunar bases might struggle to extract water from the Moon's shadowed craters, but Mercury's ice sits in relatively shallow, Sun-adjacent deposits. Imagine a day when robotic miners harvest this ice to split into hydrogen fuel and oxygen for breathable air, turning the solar system's innermost planet into a pit stop for missions venturing deeper into space. Mercury's frozen poles teach us that even in the most hellish environments, the universe finds ways to stash its most precious resource. The deeper lesson here is about cosmic balance. A planet where metal would pool like rainwater on the surface somehow hoards glaciers in its darkest corners, proving that extremes don't cancel each other out, they coexist, often side by side. Mercury's ice isn't just a scientific curiosity, it's a testament to the ingenuity of planetary physics, where geometry and gravity conspire to create oases of cold in a world forged by fire. Neutron stars are cosmic paradoxes, stellar corpses so dense that a teaspoon of their material would weigh 1 billion tons, yet their surfaces freeze at nearly negative 270 degrees Celsius, just a whisper above absolute zero. These remnants of supernova explosions pack the mass of a star into a city-sized sphere, creating gravity so intense it bends light and warps space itself. But their most jarring contradiction lies in temperature. While their cores rage at 1 trillion degrees hotter than the center of the Sun, their surfaces are among the coldest known places in the universe. This bizarre temperature split isn't just a quirk, it's a direct consequence of neutron stars' mind-bending physics. Their surfaces cool rapidly because they're essentially naked to space with no atmosphere to trap heat. Any warmth generated inside struggles to reach the surface against the crushing pull of gravity, which traps photons so effectively that heat can take years to migrate outward. The result, a surface so cold it would freeze oxygen solid, while just a few kilometers below, atomic nuclei are torn apart into a soup of quarks and gluons. What makes these frozen shells even more haunting is how they interact with the universe around them. Neutron stars often spin at dizzying speeds. Some rotate hundreds of times per second, flinging particles into space with such energy that they create beams of radiation detectable across galaxies. Yet despite this violent activity, their surfaces remain eerily cold, like a dancer spinning in a blizzard without ever feeling the snow. The only heat that does escape comes from occasional starquakes, where the star's crust cracks under gravitational stress, releasing bursts of X-rays that briefly warm tiny patches before the cold reclaims them. Scientists study these thermal contradictions to probe the limits of matter itself. The core's insane heat reveals how particles behave under pressures impossible to recreate on Earth, while the surface's deep freeze acts like a cosmic lab for quantum phenomena near absolute zero. Some theories suggest that under these extremes, neutrons in the crust might arrange themselves into bizarre, nuclear pasta shapes, spaghetti-like strands or lasagna sheets defying conventional states of matter. Neutron stars remind us that temperature isn't just about energy, it's about how that energy moves or fails to move through the fabric of reality. They're celestial refrigerators wrapped around cosmic furnaces, proving once again that the universe loves to smash our expectations. Even in death, stars find ways to rewrite the rules of physics. The void between stars isn't just empty, it's a bone-chilling abyss where temperatures dip to negative 270.45 degrees Celsius, just a hair's breadth above absolute zero. This frigid expanse owes its cold to the cosmic microwave background, the fading afterglow of the Big Bang that permeates every corner of the universe like ghostly static. Most of this chill lingers in interstellar space, far from stars that could warm it, creating an environment so hostile to heat that even the most advanced spacecraft struggle to retain warmth. Probes venturing into these regions face a paradoxical challenge. Their own electronics generate heat, but the vacuum surrounding them is too perfect to conduct it away. Without air molecules to carry thermal energy, devices can overheat while floating in a near-absolute zero void. Engineers armor deep space missions like NASA's Voyager probes with layers of gold foil and insulation, not to keep the cold out, but to trap every precious joule of warmth inside. The result, a spacecraft's interior might be cozy enough for sensitive instruments, while mere inches away, its hull faces the coldest natural environment known to science. What makes this deep space chill so unnerving is how it contrasts with Earth's most advanced artificial vacuums. Laboratory chambers on Earth can mimic the emptiness of space, but they can't replicate its temperature. Even our best pumps leave behind trace gases that subtly conduct heat. True interstellar cold only exists where matter is vanishingly rare, with just one atom per cubic centimeter compared to Earth's atmosphere's trillions. That's why the James Webb Space Telescope had to deploy a sunshield the size of a tennis court, not just to block light, but to create a pocket of shadow cold enough for its infrared sensors to peer into the cosmic depths without interference from its own warmth. Yet this extreme cold isn't just an obstacle, it's a time capsule. The cosmic microwave background's uniform temperature offers a snapshot of the infant universe, revealing patterns from when everything was compressed into a searing plasma. As photons from that era stretched across expanding space, their energy dwindled to microwave wavelengths, leaving behind this omnipresent frost. It's as if the universe never forgot its fiery birth, preserving the memory in a cold so profound it defies earthly intuition. The silent vastness between stars reminds us that temperature isn't just about energy, it's about isolation. In the crowded warmth of planetary systems, heat bounces between atoms in a constant exchange. But in the galactic voids, particles drift so far apart that warmth becomes a distant memory, leaving only the echo of creation's first light to mark the cold. It's a humbling thought. The emptiest places in existence are also the coldest, not because they lack heat, but because they've been waiting longest for warmth to find them. At -271 degrees Celsius, helium undergoes a transformation so bizarre it seems ripped from science fiction. It becomes a superfluid, capable of defying gravity and seeping through solid containers like a ghost. This isn't just extreme cold, it's matter operating under rules that feel alien to our everyday experience. When cooled to these temperatures, helium's atoms lose all friction, unlocking properties that make even quantum physicists pause in wonder. Picture a liquid that climbs upward against the pull of gravity, creeping over the rim of a glass and dripping down the outside like an upside-down waterfall. Or imagine a substance so perfectly smooth that if you stirred it, the swirl would never stop. A whirlpool with no energy loss, spinning eternally in silent defiance of the universe's tendency toward disorder. The key to this surreal behavior lies in a quantum mechanical quirk called Bose-Einstein condensation. At these frigid temperatures, helium atoms stop behaving as individual particles and merge into a single, coherent quantum state. This collective identity allows them to move in perfect unison, overcoming viscosity entirely. Experiments on Earth have captured this phenomenon in action, showing superfluid helium forming vanishingly thin films that coat every surface they touch, even scaling walls to seek out warmer regions. It's as if the fluid becomes obsessed with equilibrium, redistributing itself until every atom shares the same energy, a property that could revolutionize technologies like cryogenics or quantum computing if harnessed. But the real cosmic magic happens when we consider where else superfluidity might exist. Neutron stars, those ultra-dense remnants of supernovas, may harbor cores where neutrons, normally solitary particles, become superfluid under unimaginable pressures and temperatures. Picture a city-sized star with a crust of rigid iron-like material, beneath which trillions upon trillions of neutrons flow without resistance, creating currents that generate the star's intense magnetic fields. Some theories suggest these neutron superfluid vortices could explain sudden glitches in a pulsar's rotation, moments when the star's spin abruptly changes speed like a skipping record. What makes superfluid helium so tantalizing is how it blurs the line between the microscopic and macroscopic worlds. Here, quantum effects aren't confined to tiny particles in a lab. They manifest in a visible, tangible fluid that challenges our intuition about how matter should behave. It's a reminder that the universe's coldest places aren't just absences of heat. They're stages for some of nature's most astonishing performances, where the rules we take for granted simply don't apply. From the lab to the cosmos, superfluids whisper a tantalizing question. If matter can do this, what other impossibilities are waiting to be uncovered? Dark matter remains one of the universe's most perplexing enigmas, a substance that outweighs visible matter 5 to 1, yet refuses to interact with light or any known force except gravity. But here's where things get even stranger. This cosmic ghost might come in different thermal flavors, and whether it's cold or warm could rewrite the story of how galaxies formed. Cold dark matter, the leading theory, suggests particles moving sluggishly just a fraction of light speed, allowing them to clump easily under gravity's pull. Picture syrup dripping into water, forming dense pools that would become the seeds of galaxies. These slow-moving particles would explain why we see vast halos of dark matter enveloping galaxies like invisible cocoons, their gravity sculpting the universe's large-scale structure over billions of years. Yet some observations don't quite fit this tidy picture. Certain dwarf galaxies appear too sparse, their stars too spread out for cold dark matter's predictions. That's where warm dark matter enters the scene, particles zipping around at near light speed, too energetic to settle into dense clumps. Think of tossing a handful of sand into a fan, the grains scatter instead of piling up. Warm dark matter would leave a lighter fingerprint, explaining those diffuse galaxies but struggling to account for the universe's thick cosmic webs. The debate hinges on an impossible-sounding question. Can something invisible and intangible even have a temperature? The answer lies in dark matter's hypothetical origins. If it emerged from the early universe's chaos like a heavyweight particle, say, a hypothetical WIMP weakly interacting massive particle, it would naturally lumber along, fitting the cold model. But if it's something lighter and faster, like sterile neutrinos, its feverish motion would lean toward warmth. The James Webb Space Telescope is now peering into the universe's toddler years, hunting for tiny, faint galaxies that could tip the scales. Too many small galaxies, cold dark matter wins. Too few, warm gets a boost. This isn't just academic quibbling. The temperature of dark matter dictates how structure unfolds across the cosmos. Cold dark matter builds a universe top-down, with massive galaxies forming first and fragmenting into smaller ones. Warm dark matter flips the script, privileging small structures early on. It's the difference between constructing a skyscraper floor by floor versus assembling it from prefab modules. Even a slight thermal tweak could alter where and when stars ignite, planets coalesce, and life finds a foothold. The irony is delicious. The universe's dominant substance might owe its power not to what it is, but to how it moves. Whether dark matter is cold, warm, or some exotic hybrid, its thermal personality shapes everything we see while remaining forever in the shadows. 19 kilometers above your head lies one of Earth's most overlooked frontiers, the stratosphere, where temperatures hover around -60 degrees Celsius, a frosty buffer between the turbulent weather below and the eerie stillness of space above. This icy expanse isn't just empty air, it's a dynamic layer where chemistry and physics conspire to create a thermal paradox. While sunlight floods this altitude with ultraviolet radiation, the ozone molecules that absorb it don't warm the surrounding gas like a cozy blanket. Instead, they convert that energy into molecular motion that radiates away into space, leaving the stratosphere colder than a Siberian winter night. The ozone layer's chilling effect works like nature's air conditioning. When UV light slams into an ozone molecule, it splits apart momentarily, releasing heat that should, in theory, warm the stratosphere. But this heat doesn't stick around. It gets carried upward by infrared radiation escaping into the void, leaving the rest of the layer to shiver. This process creates a temperature inversion where the air grows colder with altitude instead of warmer, acting like a lid that traps weather systems in the troposphere below. Without this icy ceiling, storms could rise unchecked into the upper atmosphere, scrambling global weather patterns beyond recognition. Humans have touched this frigid realm through high-altitude balloons, with record breakers like the Google-sponsored Project Loon reaching stratospheric heights where temperatures dipped below -90 degrees Celsius. These balloons, often made of ultra-thin polyethylene, just a fraction of a millimeter thick, endure conditions that would shatter most materials, sweltering heat from the sun on one side while the other side faces the deep freeze of near space. In 2022, a weather balloon launched by the University of Wyoming measured temperatures so low that its sensors briefly malfunctioned, stunned by air practically devoid of thermal energy. Yet the stratosphere's cold isn't uniform. Near the poles, it plunges even further during winter, creating ice clouds so reflective they glow electric blue at twilight. These nacreous clouds, seeded by meteor dust and human-made pollutants, are more than just a spectacle. They're active participants in ozone destruction, their icy surfaces hosting chemical reactions that chew through protective ozone molecules. It's a reminder that even in this seemingly desolate layer, every degree of cold tells a story about Earth's climate machinery, humanity's footprint, and the delicate balance that keeps our planet habitable. The stratosphere's chill might seem distant, but its influence isn't. Jet streams born at its lower edge steer storms across continents, while volcanic ash trapped here can linger for years, casting shadows on crops thousands of kilometers away. This icy barrier isn't just a boundary, it's a thermostat, a chemical reactor, and a silent guardian all at once, proving that sometimes the coldest places hold the most heat for discovery. Jupiter's moon Io is a world of fire and ice locked in an eternal tug of war where lava lakes glow at 1,600 degrees Celsius, yet pockets of sulfur dioxide frost cling stubbornly to shadowed craters at -143 degrees. This ferocious temperature swing isn't just a quirk, it's the result of Io being relentlessly kneaded by Jupiter's gravity like cosmic dough. Every 42 hours as the moon orbits, tidal forces flex its crust upward by as much as 100 meters, equivalent to lifting Mount Everest in mere hours, generating enough friction to melt rock from the inside out. The result, a volcanic hellscape with over 400 active vents, some spewing plumes 500 kilometers high, while others pool into lakes of molten silicate larger than cities. These lava lakes behave unlike anything on Earth. Without plate tectonics to release pressure, Io's magma builds vast reservoirs that churn like boiling pots, their surfaces crusting over only to shatter when fresh eruptions blast through. NASA Juno spacecraft captured one such lake, Loki Patera, sprawling 200 kilometers wide, bigger than Hawaii's Kilauea caldera, with a crust that cracks and renews itself in cycles mimicking Earth's ocean tides. Infrared images reveal a surreal sight: islands of solid rock adrift in these molten seas, drifting across lake shores of slowly cooling lava. Yet just a few kilometers away from these infernos, Io's surface tells a different story. Jupiter's intense radiation strips away most of the Moon's tenuous atmosphere, leaving patches of sulfur dioxide and sulfur frost to accumulate in permanently shadowed regions. These icy deposits aren't water, they're exotic compounds that sublimate directly from solid to gas when exposed to sunlight, creating ephemeral frost geysers that briefly puff gas into space before vanishing. The real wonder lies in how these extremes coexist. Io's volcanoes constantly resurface the Moon, burying older terrain under fresh lava flows at a rate of 1 centimeter per year, meaning the entire surface could recycle itself in just 1 million years. Yet despite this geological hyperactivity, the frost patches persist, constantly replenished by volcanic outgassing that recondenses in the cold traps. It's a self-sustaining system where destruction and creation dance in lockstep, fueled entirely by gravitational friction. This tiny moon offers a glimpse into Earth's own violent past, when tidal heating may have jump-started our planet's tectonic activity. But Io's extremes also hint at possibilities beyond our solar system. Imagine exomoons orbiting gas giants in other star systems, their surfaces similarly sculpted by tidal forces into landscapes of fire and ice. Io proves that temperature isn't just about distance from a star. Sometimes it's about being caught in a gravitational embrace that refuses to let go. Brown dwarfs are the universe's cosmic in-betweeners, too massive to be planets yet too puny to ignite as full-fledged stars, simmering at temperatures ranging from a comfortable 20 degrees Celsius to a blistering 2,700. These failed stars occupy a strange twilight zone where their cores muster just enough pressure to fuse deuterium, a heavy isotope of hydrogen, but never sustain the full-blown nuclear fusion that powers suns. Picture an object 15 times heftier than Jupiter, yet its surface might feel like a mild autumn day with skies streaked by alien rainstorms. What makes brown dwarfs so fascinating isn't just their identity crisis, it's their atmospheres which defy categorization. Some, like the nearby Lumen 16 system, boast layered clouds of molten iron and salts, while others, like WISE 0855, shiver at sub-zero temperatures with water vapor and methane swirling in their skies. These methane clouds aren't like Earth's wispy cirrus formations. They're dense global blankets that trap heat like a greenhouse gone wild, creating pockets where temperatures could theoretically support liquid water, if only these worlds had surfaces to pool on. The sheer variety of brown dwarf climates reads like a catalogue of cosmic weather extremes. Warmer specimens, classified as L-types, rip apart methane molecules with their heat, leaving behind silicate clouds that rain tiny grains of sand. Cooler T-types, meanwhile, host ammonia storms that would reek like a celestial cleaning supply closet, while the chilliest Y-types, discovered only in the past decade, hover so close to planetary temperatures that their atmospheres might condense into frost mid-flight. Yet the real magic happens when these dim orbs flirt with habitability. Simulations suggest that a brown dwarf's eternal twilight, neither scorched by a star's fury nor frozen in deep space, could create stable bands where life's chemistry might tinker. Imagine organisms floating in layers where temperatures and pressures align just right, harvesting energy from atmospheric currents rather than sunlight. It's a radical twist on the concept of home, where the sky isn't a ceiling but an entire ecosystem. These misfits of the cosmos challenge our definitions of planets and stars, proving that nature doesn't care for tidy boxes. A brown dwarf might spend billions of years cooling into planet-like obscurity, its faint glow vanishing until only the echoes of its failed stellar ambitions remain. But while they last, they're living laboratories, windows into how celestial objects tread the line between flame and frost, between what could have been and what never quite was. Red supergiants like Betelgeuse defy every instinct about how stars should feel. Their surfaces simmer at a mere 3,000 degrees Celsius, cooler than some welding torches, yet they rank among the most luminous objects in the galaxy. The secret lies in their sheer scale. Stretch Betelgeuse to its full diameter, and it would swallow Jupiter's orbit whole. That massive surface area, over 1 billion times wider than the Sun's, turns what should be blistering heat into a slow, radiant glow, like holding a bonfire at arm's length instead of touching a blowtorch. Infrared telescopes reveal these stars as cosmic embers, their energy spread so thin that if you could stand on their chromospheres, the heat might feel no more intense than a desert breeze. But don't let that fool you into thinking these giants are gentle. Their relative coolness masks titanic forces beneath. Convection cells larger than solar systems churn just below the surface, carrying heat upward in sluggish waves that take years to complete a single cycle. These aren't the Sun's orderly plasma current. Imagine instead continent-sized bubbles of superheated gas bursting like lava lamps in slow motion, their turbulence so vast it distorts the star's shape into a wobbly sphere. When Betelgeuse's surface dimmed unexpectedly in 2019, astronomers realized one of these bubbles might have erupted, ejecting a dust cloud thick enough to briefly veil the star's southern hemisphere. The real thermal drama unfolds deeper down, where temperatures spike exponentially. Just a few thousand kilometers beneath that deceptively mild surface, the star's core roars at over 100 million degrees, fusing helium into carbon and oxygen with enough ferocity to outshine entire galaxies. This imbalance, a cool skin stretched over a nuclear furnace, makes red supergiants ticking time bombs. Their outer layers puff outward like cotton candy, so loosely bound that gravity barely holds them, while the core prepares for its inevitable collapse into a supernova. When that happens, the star's surface temperature will skyrocket in seconds, transforming from 3,000 to over 100,000 degrees as the shockwave tears through. What makes these stars so mesmerizing isn't just their size or eventual fate. It's how they redefine our perception of heat. A candle flame at 2,000 degrees Celsius would vaporize your hand, yet Betelgeuse's surface, half again as hot, feels cosmically chilly because its energy diffuses across such an absurd volume. It's a reminder that temperature alone doesn't dictate intensity. Context is everything. From a distance, these crimson behemoths seem almost cozy, their light tinged orange-red like a perpetual sunset. But up close, they're monsters wearing the thermal equivalent of a poker face, calm on the outside, apocalyptic beneath. White dwarfs are stellar tombstones, super-dense remnants of stars like our Sun that exhausted their nuclear fuel and collapsed into objects no larger than Earth, yet packing 500,000 times its mass. Their surfaces blaze at 10,000 degrees Celsius, hot enough to vaporize diamonds, while their cores crystallize into exotic forms of degenerate matter over trillions of years. Sirius B, the nearest known white dwarf, exemplifies this paradox, a dying ember glowing brighter than the Sun per square inch, its carbon core slowly compressing into a structure akin to a galaxy-sized diamond. What makes these objects so astonishing isn't just their heat, it's how they defy conventional cooling. Unlike a campfire fading to ashes, white dwarfs are wrapped in degenerate electron gas, a quantum mechanical state where particles resist compression so fiercely that heat struggles to escape. Picture a thermos bottle forged by stellar physics. Their brilliant surfaces radiate energy into space, but the interior remains so insulated that a white dwarf could outlast the current age of the universe before freezing solid. Even after 14 billion years, the oldest white dwarfs still sizzle at thousands of degrees, their light eerily persistent against the cosmic cold. The crystallization process deep inside them is even more surreal. As temperatures drop below 8 million degrees, carbon and oxygen ions arrange themselves into orderly lattices, releasing latent heat that briefly reheats the star, like water releasing warmth as it freezes, but on a stellar scale. Some models suggest the cores may eventually solidify into metallic oxygen surrounding crystalline carbon, creating a stratified structure reminiscent of a cosmic jawbreaker. The denser white dwarfs might even form neutron-rich ice layers where electrons merge with protons to create neutrons under the crushing pressure. Sirius B offers a tantalizing preview of our Sun's fate. In 7 billion years, after swelling into a red giant and shedding its outer layers, the Sun's exposed core will similarly contract into a white dwarf. But here's the twist: its eventual diamond core won't be pristine. Current theories suggest convection currents might stir the crystallizing material like a sluggish lava lamp, creating dynamic patterns in the crystal matrix that could persist for eons. These dead stars aren't just relics, they're timekeepers. By measuring their cooling rates, astronomers can date the Milky Way's oldest regions. Their faint light whispers secrets about stellar evolution, quantum physics under extreme conditions, and even the ultimate fate of matter. A white dwarf's brilliance today is a fleeting spark against the darkness, but its cold, crystalline heart beats with the patience of eternity. The Sun's corona is one of the most baffling thermal paradoxes in our solar system, a shimmering halo of plasma that burns between 1 and 3 million degrees Celsius while the surface below simmers at a relatively tepid 5,500. Picture holding a candle where the flame stays cool, but the glow around it could vaporize steel. This defiance of common sense has puzzled scientists for decades because, according to basic thermodynamics, heat shouldn't flow from a cooler surface to a hotter atmosphere any more than water should run uphill. The leading suspect behind this cosmic heating mystery is the Sun's tangled magnetic field. Unlike Earth's relatively orderly magnetic lines, the Sun's field is a chaotic web, constantly twisting and snapping like overstretched rubber bands. When these lines break and reconnect, a process called magnetic reconnection, they release explosive bursts of energy, accelerating charged particles to near light speeds. Think of it as a celestial game of crack the whip, where strands of magnetism suddenly whip together, transferring enough energy in milliseconds to heat the surrounding plasma to millions of degrees. NASA Parker Solar Probe, flying closer to the Sun than any spacecraft before it, has detected nanoflares, tiny versions of these eruptions popping off constantly like popcorn in a cosmic microwave, collectively dumping enough heat into the corona to maintain its furnace-like temperatures. But magnetic reconnection isn't the only theory. Some researchers point to Elfvane waves, ripples in the Sun's magnetic field that carry energy outward like vibrations along a plucked guitar string. These waves might channel heat from the Sun's churning interior into the corona, though how they deposit that energy so efficiently remains a puzzle. Others speculate that the corona's tenuous nature plays a role, with particles so spread out they can't easily collide and dissipate energy, letting them stay scorching hot even as the denser surface below cools through constant interaction. The corona's heat has real consequences beyond scientific curiosity. It's the engine behind the solar wind, the stream of charged particles that bathes the entire solar system. When particularly violent coronal heating triggers mass ejections, the resulting geomagnetic storms can knock out satellites and power grids on Earth. Understanding this layer isn't just about solving a thermal riddle, it's about predicting space, whether that could one day mean the difference between a connected civilization and a global blackout. What makes the corona so mesmerizing is how it upends our expectations. A star's atmosphere shouldn't be hundreds of times hotter than its surface, yet the Sun casually defies that logic every second. It's a reminder that even the most familiar objects in the sky still harbor secrets, waiting for probes like Parker to fly through the flames and bring back answers. Jupiter's lightning doesn't just crackle, it detonates with the fury of a solar flare, reaching temperatures of 30,000 degrees Celsius, 5 times hotter than Earth's most violent thunderstorms. These aren't mere sparks in the gas giant's atmosphere. They're cataclysmic discharges that could vaporize a spacecraft in milliseconds. What makes them even more alien is their fuel. Not the water vapor that drives terrestrial storms, but slushy mixtures of ammonia and water churned into fury by Jupiter's relentless atmospheric turbulence. NASA Juno spacecraft caught these superbolts in action, revealing bolts so energetic they briefly outshine the planet's reflective clouds in ultraviolet light. But here's where Jupiter's lightning gets truly bizarre. Some of it originates far higher in the atmosphere than scientists thought possible. Dubbed shallow lightning, these flashes erupt from clouds where temperatures hover around -88 degrees Celsius, so cold that ammonia acts like antifreeze, preventing water droplets from freezing solid. Instead, they form a mushy ammonia-water slurry that builds up explosive electrical charges as it collides with rising and sinking gases. When the tension snaps, the resulting bolts fork through Jupiter's upper atmosphere like jagged rivers of plasma, visible from space as fleeting bright spots against the planet's swirling bands. Juno's sensitive microwave radiometer peeled back another layer of the mystery. These storms aren't confined to Jupiter's dark side, as once assumed. They rage equally in daylight, just hidden beneath cloud tops so thick their glow gets smothered. The spacecraft even detected mushballs, hailstone-like chunks of ammonia-water ice that form in these storms, dragging heavier compounds like ammonium hydrosulfide deep into Jupiter's interior. It's a far cry from Earth's relatively tame weather, where lightning follows predictable paths and hail melts before hitting the ground. The scale of these electrical storms defies imagination. Some Jovian lightning supercells span continents, their anvil clouds towering over 60 kilometers high, 3 times taller than Everest. Instead of lasting minutes like Earth's thunderstorms, they persist for days, even weeks, fueled by heat welling up from Jupiter's scorching interior. And while our planet averages about 40 lightning strikes per second globally, scientists estimate Jupiter's count could be 1,000 times higher, turning entire latitudes into non-stop light shows. What makes these discoveries so thrilling isn't just their spectacle, it's what they reveal about atmospheric physics under extreme conditions. Jupiter's lightning operates by rules that challenge our terrestrial playbook, proving that nature's creativity doesn't stop at Earth's edge. As Juno continues its orbits, each pass peels back more secrets about how this giant's chaotic weather machine works, one electrifying flash at a time. When a massive star breathes its last, it doesn't fade quietly, it detonates with a fury that eclipses entire galaxies, unleashing temperatures of 100 billion degrees Celsius in its shockwave. That's over 6,000 times hotter than the Sun's core, a thermal spike so intense it can forge gold, uranium, and other heavy elements in seconds. Supernovas don't just die, they transform into cosmic alchemists, their final moments rewriting the periodic table. The clues to this inferno aren't just written in light, they're carried by ghostly particles called neutrinos. When supernova 1987 lit up the Large Magellanic Cloud in 1987, detectors on Earth caught a burst of these elusive particles 3 hours before the visible explosion. That's because as the star's core collapsed, trillions of neutrinos blasted outward at near light speed, slipping effortlessly through the star's outer layers while photons of light still fought to escape. Those 20 or so neutrinos captured by human instruments represented a fraction of the octodecillion. That's one followed by 57 zeros that flooded the solar system in a 10-second pulse, carrying with them a snapshot of conditions hotter than anything the sun could ever produce. What makes these shockwaves so astonishing is how they warp the very fabric of nuclear physics. At 100 billion degrees, atomic nuclei don't just melt. They disintegrate into a primordial soup of quarks and gluons, the same state the universe existed in a microsecond after the Big Bang. Protons and neutrons dissolve like sugar in boiling water, their components set free in a frenzy of particle collisions. As the shockwave expands, it cools just enough to let these particles reconfigure into new, heavier elements, scattering them across interstellar space like seeds for future planets and life. Yet even this unimaginable heat is fleeting. Within minutes, the shockwave's temperature plummets by orders of magnitude as it plows through the star's outer layers, creating the dazzling light show we observe. The real legacy of that 100 billion degree inferno isn't the flash, it's the heavier elements forged in the crucible, the same ones that now course through our veins and form the ground beneath our feet. Every time you inhale oxygen or wear a gold ring, you're touching the aftermath of a heat so extreme it defies mortal comprehension, proof that even in death, stars give birth to the building blocks of existence. At 4 trillion degrees Celsius, ordinary matter doesn't just break apart, it unravels into its most fundamental building blocks, a state so extreme it hasn't existed naturally since the first microseconds after the Big Bang. This is quark-gluon plasma, a searing soup where protons and neutrons dissolve into their constituent quarks and gluons, particles normally bound so tightly by the strong nuclear force that isolating them was once thought impossible. CERN's Large Hadron Collider doesn't just study this plasma, it recreates it, slamming lead nuclei together at 99.9999% the speed of light to mimic the universe's fiery birth. The moment of creation is breathtakingly brief. When those ultra-relativistic lead ions collide, they compress into a speck 10,000 times hotter than the sun's core, but smaller than an atom. For less than a trillionth of a second, quarks and gluons, normally shackled inside protons by nature's strongest force, roam freely like molecules in a liquid. Detectors surrounding the collision point capture the aftermath, a shower of particles revealing how this primordial fluid flowed, its viscosity so low it's been dubbed the perfect liquid. Unlike water or lava, quark-gluon plasma barely resists deformation, its behavior defying classical physics to follow quantum rules written when the universe was younger than a heartbeat. What makes this plasma so revolutionary isn't just its heat, it's how it reshapes our understanding of cosmic history. In those first microseconds after the Big Bang, the entire universe existed in this state, a superheated medium where today's familiar matter was impossible. As space expanded and cooled, quarks and gluons finally froze into protons and neutrons like water crystallizing into ice. By recreating these conditions, physicists are effectively running the universe's tape backward, glimpsing the exact moment structure emerged from chaos. But the surprises don't stop there. This plasma behaves nothing like scientists originally predicted. Instead of a dilute gas of weakly interacting particles, it flows with near-perfect fluidity, suggesting quarks and gluons interact far more intensely than expected even when free. Some theories now propose that under even higher temperatures, perhaps those reached in neutron star mergers, this plasma might transition into an entirely new phase, one where quarks pair up in ways that defy current models. Every collision at CERN is a miniature Big Bang, a fleeting window into a time when the universe was too hot for atoms, stars, or even the laws of physics as we know them. The fact that we can recreate these conditions in a lab, however briefly, is a testament to human curiosity and a reminder that the most extreme temperatures in existence aren't just out there in the cosmos. Sometimes they're hiding in plain sight beneath the serene countryside of Switzerland and France, waiting for us to unlock their secrets. Magnetars take the concept of extreme heat and crank it to ludicrous levels. These neutron stars occasionally unleash flares reaching 100 trillion degrees Celsius, making them the hottest transient events in the known universe. To put that incomprehensible number in perspective, it's over 6 million times hotter than the core of a supernova. These eruptions don't just burn, they rewrite the laws of physics, producing energy so intense that a single flare lasting 1/10 of a second can outshine every star in our galaxy combined. The source of this apocalyptic heat lies in magnetar's unimaginably twisted magnetic fields. Imagine taking Earth's magnetic field and compressing it into a sphere the size of Manhattan. That's the baseline for these cosmic monsters. Their fields are so strong they strain the fabric of space-time, creating visible distortions called quantum tornadoes where the magnetic lines snap and reconnect. When these lines finally break under the stress, they release pent-up energy in the form of gamma ray, bursts so bright they've been detected from 50,000 light-years away, momentarily blinding satellites designed to study cosmic explosions. One such burst from magnetar SGR 1806-20 actually ionized Earth's upper atmosphere in 2004 despite erupting halfway across the Milky Way. The flare carried enough energy to power human civilization for 500,000 years, all expended in a blink. What's terrifying is that these eruptions aren't rare quirks. Magnetars experience starquakes where their rigid crusts crack under magnetic pressure, triggering cascades of X-rays and gamma rays. NASA Fermi telescope has recorded these quakes as rhythmic pulsations, like a celestial drumbeat heralding destruction. Yet for all their fury, magnetars are paradoxically fleeting. Their magnetic fields decay within 10,000 years, a cosmic eye blink, leaving behind a quieter neutron star. This means we're catching these objects in their most violent, unstable phase, like witnessing a volcano mid-eruption. Their existence hints at even wilder possibilities. Some theorize the Big Bang itself may have birthed similar magnetic monsters in its first seconds, their flares so hot they briefly rivaled the temperature of creation. What makes magnetars truly humbling is how they stretch our understanding of heat itself. At 100 trillion degrees, matter doesn't just ionize, quarks and gluons dissociate into a plasma where the very concepts of temperature and energy blur. These flares are less like fires and more like temporary holes in reality, windows into a realm where physics as we know it starts to unravel. And somewhere in the cosmos right now, another magnetar is winding up for its next cataclysmic release, a reminder that the universe's furnace still has settings we've yet to fully comprehend. Picture the universe in its first trillionth of a second, a seething, unimaginable forge where temperatures hit 100 million trillion degrees Celsius. This wasn't just extreme heat, it was the energy threshold where the very concepts of space and time began to wobble. During cosmic inflation, the universe didn't just expand. It exploded outward faster than light itself, stretching from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. At these temperatures, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were fused into a single, unified superforce. Matter as we know it couldn't exist yet. There was only a roiling quantum foam where particles flickered in and out of existence, borrowing energy from nothingness before vanishing again. The heat of this era wasn't just a side effect, it was the engine of creation. As space stretched at speeds defying Einstein's cosmic speed limit, quantum fluctuations in this primordial soup got stretched along with it. Tiny ripples smaller than subatomic particles ballooned into vast density variations, seeding the future galaxies, stars, and planets we see today. It's like blowing up a balloon with microscopic dots drawn on its surface. By the time it's fully inflated, those dots have become continents. The European Space Agency's Planck satellite has mapped the faint echoes of these fluctuations in the cosmic microwave background, revealing patterns that match theoretical predictions with stunning precision. What makes this heat so mind-bending is how it warps our understanding of physics. At 10 to the 32 degrees, even quantum fields started behaving strangely. The Higgs field responsible for giving particles mass hadn't yet condensed into its modern state. Particles moved at these temperatures were effectively massless, zipping around at light speed without the drag of inertia. Some theories suggest the universe might have undergone a phase transition during this period, like steam cooling into water, releasing latent energy that further fueled inflation's runaway expansion. Yet the most astonishing relic of this era isn't the heat itself, it's the quantum foam, a frothy, churning spacetime at scales a trillion times smaller than an atom. In this foam, virtual particles popped into existence with enough energy to briefly warp gravity itself, creating microscopic wormholes and tunnels that vanished almost instantly. These fleeting distortions might hold clues to a theory of quantum gravity, bridging the gap between Einstein's relativity and quantum mechanics. Experiments with particle colliders and gravitational wave detectors are now hunting for echoes of this foam in the modern universe, like archaeologists sifting for cosmic fossils. The heat of cosmic inflation didn't just shape the universe, it set the rules for everything that followed. Without that blistering, faster-than-light expansion, galaxies might never have formed, and the cosmos could have been a featureless void. It's a humbling thought. Every atom in your body, every star in the sky, owes its existence to a split-second inferno where the laws of physics as we know them were still being written. And somewhere in the quantum static of deep space, the faintest tremors of that epoch might still resonate, waiting for us to decode their secrets. Venus doesn't just flirt with extreme heat, it drowns in it, trapped in a runaway greenhouse effect so severe its surface hovers at 465 degrees Celsius, hot enough to liquefy lead. This isn't just a planetary heat wave, it's a cautionary tale of climate gone haywire, a world where thick carbon dioxide clouds act like a one-way thermal blanket, letting sunlight in but refusing to let heat escape. The irony is cruel. Venus, named for the goddess of love, is a scorched wasteland where spacecraft survive mere hours before succumbing to the crushing pressure and corrosive atmosphere. The roots of this inferno lie in a fateful feedback loop. Billions of years ago, Venus might have even resembled early Earth with oceans and a temperate climate. But as the sun grew brighter, Venus's proximity triggered a catastrophe. Water vapor, a potent greenhouse gas, built up in its atmosphere, trapping more heat and evaporating its oceans. The steam intensified the warming, baking carbonates out of rocks and pumping even more carbon dioxide into the air. Unlike Earth, where plate tectonics and oceans recycle carbon over millennia, Venus had no escape valve. Its greenhouse gases accumulated unchecked, turning the planet into a pressure cooker where surface temperatures now exceed those of Mercury, despite being nearly twice as far from the Sun. Those yellowish clouds swirling 50 kilometers above Venus's surface aren't made of water, they're a toxic brew of sulfuric acid droplets, reflecting sunlight with an eerie glow while contributing to the planet's suffocating insulation. The European Space Agency's Venus Express orbiter discovered something even stranger. These clouds host mysterious dark patches that absorb ultraviolet light, possibly hinting at unknown chemical reactions or even microbial life clinging to the acidic haze. It's a tantalizing thought that life, if it exists, might thrive not on the hellish surface but in the cooler, though still deadly, cloud decks. The contrast with Earth couldn't be starker. Both planets started with similar ingredients, but Earth's carbon cycle, a delicate dance of volcanoes, weathering, and oceans, kept our climate in balance. Venus lost its water, and without liquid oceans to dissolve carbon dioxide and lock it into rocks, the gas built up relentlessly, the terrifying lesson. A planet's climate is fragile. Venus shows us what happens when greenhouse gases tip past the point of no return, transforming a once hospitable world into a blistering purgatory. Yet Venus isn't just a warning, it's a laboratory. Scientists study its atmosphere to refine climate models, testing how well we understand feedback loops that could one day threaten Earth. Recent probes like NASA Da Vinci aim to plunge through its clouds, measuring gases that could reveal how and when Venus's climate spiraled out of control. Every new discovery peels back another layer of this planetary mystery, reminding us that extreme heat isn't just a number, it's the story of a world that took a wrong turn and the secrets it holds about our own. Mercury's sunlit side isn't just hot. It's a furnace with no mercy where temperatures rocket to 430 degrees Celsius, enough to melt zinc into shimmering puddles. This blistering heat comes from sitting closer to the Sun than any other planet, but the real culprit is Mercury's tragic lack of atmosphere. Unlike Venus or Earth, where clouds and air spread heat like a cosmic blanket, Mercury's surface bakes under raw solar radiation with nothing to soften the blow. The result, daylight so intense it would vaporize water in seconds, while shadows just a few meters away plunge into sub-zero darkness. The absence of atmosphere creates thermal whiplash unlike anywhere else in the solar system. On Earth, air molecules constantly collide, distributing warmth from day to night. But Mercury's near vacuum means heat has no way to travel, no wind, no weather, just brutal stillness. A rock in sunlight could sizzle at oven temperatures while its shaded side chills to negative 180 degrees Celsius, all within the same square meter. NASA's messenger orbiter mapped these extremes, revealing landscapes where cliffs cast knife-edge shadows so sharp they look painted onto the surface. Surviving these conditions sounds impossible, yet NASA's Parker solar probe routinely endures even worse, swooping within 6 million kilometers of the Sun's corona, where temperatures exceed 1 million degrees. The secret: cutting-edge materials and clever engineering. Parker's white ceramic heat shield reflects 97% of incoming sunlight, while a carbon foam core insulates its instruments like a thermos in a bonfire. Its solar arrays even retract like origami to avoid frying, peeking out only when the probe reaches safer distances, but Mercury lacks such protection naturally. Its surface isn't just hot, it's chemically transformed by the onslaught. The planet's dark gray color comes from eons of solar wind blasting its rocks into a dusty coating called space weathering. Unlike the Moon, where impacts churn up fresh material, Mercury's heat bakes this layer into a permanent tan, leaving it darker than it should be for its composition. The cosmic irony is that Mercury's proximity to the Sun also offers salvation. Those same solar forces that blast its day side likely help maintain ice in permanently shadowed craters, creating a world of juxtaposed extremes. It's a reminder that in space, heat isn't just about temperature, it's about what stands between you and the fire. Kelt 9b isn't just an exoplanet, it's a celestial demolition derby where molecules get ripped to shreds under a 4,300 degrees Celsius onslaught. This hot Jupiter orbits so close to its host star that a year lasts just 36 hours, and its day side is literally hotter than some red dwarf stars. The radiation here is so intense that even titanium and iron metals that would happily pool into molten lakes on cooler worlds exist as vapor, condensing only on the planet's eternally dark night side before raining back down as metallic droplets. The violence begins with Kelt 9b star, a blue giant burning at nearly 10,000 degrees Celsius, almost twice as hot as our Sun. Locked in a death grip just 4.5 million kilometers away, Mercury, by comparison, orbits 36 times farther from our Sun. The planet's atmosphere is being blasted into space at a rate of 10,000 tons per second. Hydrogen gas streams off like a comet's tail, creating an envelope so distended that the planet balloons to nearly 3 times Jupiter's size despite having half its mass. Hubble Space Telescope observations caught this evaporation in action, revealing spectral lines of iron and titanium so charged up they resemble a cosmic fingerprint of atomic disintegration. But the real spectacle happens at the boundary between day and night. The planet's tidal locking means one side always faces the star while the other drowns in eternal darkness. On the day side, temperatures shatter molecular bonds, breaking water vapor into oxygen and hydrogen atoms, and titanium oxide into its constituent metals. These free atoms then ride atmospheric winds reaching 7 kilometers per second, 20 times hurricane force toward the night side. As they cross into darkness, the temperature plummets by 2,000 degrees, allowing titanium and iron to recombine into microscopic droplets that fall as surreal metallic rain. The planet's composition reads like an alchemist's fever dream. Spectroscopy reveals gases like atomic iron, singly ionized titanium, and even traces of rare Earth elements, all normally buried deep in planetary interiors. This exposed innards creates an atmosphere more akin to a star's outer layers than a planet's, with ionized gases glowing under the stellar onslaught. Some astronomers speculate Kelt 9b might eventually evaporate entirely, leaving behind a ghostly core of refractory metals too stubborn to vaporize a planetary skeleton forged in the harshest furnace imaginable. What makes this world so mesmerizing isn't just its extremes, it's what it reveals about planetary resilience. Kelt 9b defies expectations by existing at all, surviving where theory suggested gas giants should be torn apart. Its tortured existence pushes the boundaries of what we consider a planet, blurring the line between failed stars and doomed worlds. Every molecule that escapes its gravity, every metallic raindrop that plummets back to its surface, writes a new chapter in our understanding of how planets live and die under the cruelest stars. At 15 million degrees Celsius, the cores of collapsing protostars cross a threshold where chaos becomes creation, where random churning transforms into the ordered fury of nuclear fusion. This metamorphosis begins in stellar nurseries like the Orion Nebula, where vast clouds of hydrogen and helium laced with cosmic dust succumb to gravity's relentless pull. As these gas pockets contract, their centers grow denser and hotter, compressing atoms until they jostle with enough violence to overcome their natural repulsion. When temperatures hit that critical 15 million degree mark, protons slam together with such force that they fuse into helium, unleashing the same process that powers every star in the sky. Herbig-Haro objects are the universe's way of marking these fiery births. These glowing knots of gas, named after astronomers George Herbig and Guillermo Haro, act like cosmic road signs pointing to newborn stars. Picture a protostar still swaddled in its natal cloud, guzzling material so fast that it can't digest it all smoothly. The excess gets funneled into twin jets shooting outward at 500,000 kilometers per hour stellar tantrums that slam into surrounding gas, heating it until it glows like neon. Hubble's images of HH objects reveal these shockwaves in psychedelic detail. Twisted ribbons of ionized hydrogen and oxygen stretching light years into space, painted in hues of blue and red by their extreme temperatures. The physics behind this transformation is as elegant as it is violent. As the protostar's core contracts, it doesn't heat uniformly. Like a pot of water nearing a boil, convection currents stir the plasma, creating pockets where fusion ignites sporadically before stabilizing into a sustained reaction. Energy from these first fusions floods outward, halting the star's collapse in a delicate equilibrium where gravity's inward pull balances against radiation's outward push. This tipping point, known as the Hayashi track, marks the moment a collapsing cloud officially becomes a star, though it'll take millions more years to settle into the hydrogen-burning stability of adulthood. What makes Herbig-Haro objects so invaluable to astronomers isn't just their beauty, it's their transparency. Unlike mature stars shrouded in their own brilliance, these jets let scientists peer directly into the engine of stellar birth. The jet's spectra reveal shock temperatures exceeding 10,000 degrees, while their structures hint at magnetic fields powerful enough to sculpt gas into narrow beams. Some HH objects even exhibit knots of material that pulse outward in waves, like footsteps in the snow tracing a sprinter's path, offering clues about how protostars feed in fits and starts. The journey from cold, dark cloud to fusion-powered star isn't a gentle one. It's a battle against entropy, a defiance of dispersion where heat is both the weapon and the prize. Every newborn star we see, whether in the Orion Nebula or a distant galaxy, was once a seething core fighting to ignite. its birth cries etched into the cosmos as glowing Herbig harrow trails. These objects remind us that creation in the universe isn't just serene nebulae and quiet orbits sometimes. It's a 15 million degree inferno where the fate of worlds is decided one atomic collision at a time. Deep in the sun's core, where temperatures reach a staggering 15 million degrees Celsius, a delicate atomic ballet unfolds, one that turns hydrogen into helium and lights up our entire solar system. This proton-proton chain reaction, the universe's most fundamental power source, begins when 4 hydrogen nuclei overcome their natural repulsion through sheer thermal violence, fusing into a single helium atom while releasing a burst of energy that takes 100,000 years to journey from core to surface. Each second, the Sun converts 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons transformed into pure energy according to Einstein's famous equation E equals mc squared. That's equivalent to detonating 90 billion megatons of TNT every single second. Now contrast this with Earth's core, a relatively temperate 6,000 degrees Celsius, barely a warm glow compared to the Sun's thermonuclear furnace. Our planet's inner heat comes not from fusion but from radioactive decay of elements like uranium and thorium, mixed with residual warmth from Earth's violent formation 4.5 billion years ago. Yet even these modest temperatures create enough thermal energy to drive plate tectonics, generate our magnetic field, and keep our outer core molten. The difference between 15 million and 6,000 degrees isn't just quantitative, it's the gap between chemistry and nuclear physics, between a planet's simmer and a star's self-immolation. Scientists recreate slices of these extreme conditions using diamond anvil cells, devices that squeeze materials between 2 flawless diamonds to pressures exceeding 3 million atmospheres. While they can't match the Sun's core temperatures, these experiments have achieved 4,000 degrees Celsius, hot enough to make water behave like a metal or turn hydrogen into a shimmering solid. In 2016, researchers even observed deuterium undergoing partial fusion at room temperature under extreme pressure, offering glimpses into how quantum tunneling allows protons to fuse despite their electromagnetic repulsion. What makes the Sun's core reactions so astonishing is their improbable efficiency. At 15 million degrees, protons move fast enough to collide frequently, but quantum mechanics plays the real hero, allowing particles to tunnel through barriers that classical physics says should repel them. Without this quantum fluke, stars would need temperatures 10 times hotter to ignite fusion. The proton-proton chain isn't just a powerhouse, it's a cosmic cheat code, bending the rules just enough to make life possible. From Earth's slowly cooling heart to the Sun's relentless inferno, these temperature extremes aren't just numbers, they are the architects of existence itself. The same quantum quirks that let stars shine also ensure our planet remains habitable, proving that the universe's thermal palette spans from the barely molten to the cosmically catastrophic, all fine-tuned to build worlds where atoms can dream. Blue supergiants like Rigel are the rock stars of the cosmos, brilliant, volatile, and doomed to burn out fast, with surface temperatures soaring past 50,000 degrees Celsius. These colossal stars pump out ultraviolet radiation so intense it can ionize entire nebulas, stripping electrons from atoms light years away. Rigel, the left foot of Orion, shines 85,000 times brighter than our Sun despite being 860 light-years distant. If placed at the center of our solar system, its searing UV output would vaporize Earth's atmosphere in days, turning our blue marble into a charred cinder. What makes these blue behemoths so fascinating isn't just their heat, it's their explosive lifespans. While our Sun will chug along for 10 billion years, Rigel and its ilk live fast and die young, exhausting their nuclear fuel in just 10 million years. Their cores operate like overclocked fusion reactors, fusing helium into carbon and oxygen at breakneck speeds to withstand gravity's crushing grip. This reckless energy expenditure stretches their outer layers into bloated, turbulent atmospheres where magnetic fields whip plasma into gargantuan loops. Hubble images reveal Rigel's surface speckled with convective cells larger than our entire star, each one a roiling storm of superheated gas. The death of a blue supergiant is where the real cosmic drama unfolds. When their cores finally exhaust fusible material, gravity wins in a catastrophic collapse, triggering supernovas that can briefly outshine their host galaxies. These aren't just any stellar explosions. Blue supergiant supernovas produce some of the most energetic blasts in the universe, known as Type Roman 2L or Type Ib events. Their light curves show abrupt dips and spikes as shockwaves interact with layers of previously ejected material, a signature of the star's violent pre-death convulsions. Scientists keep close watch on potential supernova candidates like Eta Carinii, a volatile blue variable star that's already ejected 30 solar masses in spectacular outbursts. When it finally detonates, possibly within the next 100,000 years, the blast could shower Earth with enough gamma radiation to disrupt our ozone layer. Yet this same destructive potential seeds the cosmos with heavy elements. The gold in your jewelry, the calcium in your bones, even the oxygen you breathe, all were forged in supergiant furnaces and scattered across space by their explosive demises. These stars also serve as cosmic lighthouses for probing the universe's expansion. Their predictable brightness patterns allow astronomers to measure intergalactic distances, helping calibrate the Hubble constant. But perhaps their greatest lesson is one of impermanence, a reminder that even the universe's most radiant giants are fleeting, their brilliance a prelude to the darkness they'll one day leave behind. Wolf-Rayet stars are cosmic demolition crews, dying giants so ferocious they blast away their own atmospheres at 6 million kilometers per hour, exposing nuclear fusion byproducts to the void. These stellar rebels burn at 200,000 degrees Celsius on their exposed surfaces, making them some of the hottest normal stars in the universe. Unlike our Sun's relatively placid hydrogen-burning existence, Wolf-Rayet stars have already peeled back their outer layers like an onion shedding skin, revealing the carbon, oxygen, and heavier elements cooked up in their cores. Their spectra read like a chemist's fever dream, dominated by helium, nitrogen, or carbon emission lines instead of the usual hydrogen signatures, stellar fingerprints shouting their advanced stage of evolution. Take WR-142 in the constellation Cygnus, a searing ball of ionized oxygen and carbon just 15 times wider than Earth but 80 times the Sun's mass. This star's ultraviolet radiation is so intense it strips electrons from atoms light years away, creating a glowing bubble of plasma around it. Hubble images show its supersonic stellar wind colliding with interstellar gas, sculpting shockwaves that ripple outward like cosmic graffiti. These winds aren't gentle breezes, they're apocalyptic outflows carrying a sun's worth of material into space every 100,000 years, enough to seed future star systems with heavy elements. What truly sets Wolf-Rayet stars apart is their role as galactic alchemists. In their final death throes, they're destined to explode as Type Ib or Ike supernova, spectacular blast lacking hydrogen signatures because they've already ejected those outer layers. These explosions forge elements like gold, platinum, and uranium through rapid neutron capture, scattering them across interstellar space. The famous Crab Nebula's pulsar likely began as a Wolf-Rayet star, its supernova observed by Chinese astronomers in 1054 AD. Yet these stars aren't just destructive, they're creative. Their fierce winds and eventual supernova compress nearby gas clouds, triggering new star formation even as they obliterate their surroundings. It's a stellar paradox, life-giving and life-ending forces woven together by the same celestial objects. When you inhale oxygen or wear a gold ring, you're touching the legacy of Wolf-Rayet stars, the universe's way of turning stellar death into the building blocks of planets and life. Pulsar wind nebulae are cosmic powerhouses where the raw fury of a spinning neutron star gets channeled into surrounding gas, superheating it to 10 million degrees Celsius, hot enough to glow fiercely in X-rays. At the heart of these nebulas lies a pulsar, the crushed core of a star that went supernova, now spinning hundreds of times per second and flinging charged particles outward at nearly the speed of light. These high-energy electrons and protons collide with slower-moving gas and dust, transferring so much energy that the entire region lights up like a celestial blast furnace. The result, a shimmering, high-energy bubble where temperatures rival the sun's core, but span volumes large enough to swallow entire solar systems. The Crab Nebula, just 6,500 light-years away, is the perfect case study. Born from a supernova witnessed by Chinese astronomers in 1054 AD, its core harbors a pulsar spinning 30 times per second, so precise it's been called the universe's most accurate clock. Every rotation, this pulsar whips its magnetic field around like a lighthouse beam, accelerating particles until they radiate across the electromagnetic spectrum. X-ray telescopes reveal the nebula's intricate inner structure, jets of particles shooting from the pulsar's poles, shockwaves rippling through the expanding gas, and a luminous torus of material encircling the star's equator. The most energetic particles create a blue-white glow in visible light, while the X-rays trace even hotter regions where temperatures soar past 10 million degrees. What makes pulsar wind nebulae so mesmerizing isn't just their heat, it's the physics behind their glow. Unlike a campfire that radiates heat in all directions, these nebulas shine because of synchrotron radiation, a process where particles spiraling around magnetic field lines emit light. The faster the electrons move, the higher the energy of the emitted photons, which is why the Crab Nebula's core blazes in X-rays while its outer edges emit lower energy radio waves. This same mechanism powers some of the most extreme objects in the universe, from supermassive black holes to distant quasars. Yet the Crab Nebula is more than a pretty light show. Its pulsar wind carries enough energy to reshape the surrounding nebula, carving out cavities and sculpting tendrils of gas. Over centuries, these winds have accelerated the nebula's expansion to over 1,500 kilometers per second, fast enough to cross the continental United States in under 3 seconds. Even more astonishing, the total power output of the Crab's pulsar rivals that of the Sun, despite being just a few kilometers wide. It's a reminder that in the cosmos, size doesn't dictate strength. Sometimes the smallest objects wield the most devastating energy. For astronomers, these nebulas are natural laboratories for studying particle acceleration and magnetic fields under conditions impossible to recreate on Earth. The Crab's pulsar, for instance, has helped scientists test Einstein's theory of general relativity, as its precise timing reveals subtle gravitational effects. Future observations may even uncover how pulsar winds contribute to galactic ecology, seeding interstellar space with high-energy particles that could influence star formation. From their violent births to their enduring brilliance, pulsar wind nebulae are monuments to the universe's ability to transform destruction into dazzling light. At the heart of every massive galaxy lurks a gravitational monster so powerful it can warp space itself, the supermassive black hole. But it's not the black hole's darkness that dazzles astronomers, it's the white-hot fury of its surroundings, where temperatures spike beyond 100 million degrees Celsius. This nightmare furnace, called an active galactic nucleus, transforms simple matter into the most luminous objects in the universe, quasars that outshine entire galaxies from billions of light-years away. The heat originates in the accretion disk, a swirling maelstrom of gas, dust, and doomed stars spiraling toward oblivion. As material falls inward, friction between particles converts motion into heat with terrifying efficiency, like a cosmic blender churning at relativistic speeds. The inner edges of these disks move so fast, approaching light speed, that atoms get torn apart into a plasma of electrons and atomic nuclei, glowing fiercely across the electromagnetic spectrum. X-ray telescopes reveal this radiation as searing pulses, each photon carrying enough energy to strip electrons from solid metal at a distance. Yet the real thermal spectacle happens above and below the disk, where twin jets of plasma scream outward at 99% light speed. These relativistic jets, channeled by the black hole's spin and magnetic fields, create shockwaves heated to billions of degrees where they slam into interstellar gas. The process resembles a blowtorch hitting a glacier, except the torch is several light years long, and the steam it produces glows in gamma rays. Some jets extend for millions of light years, punching clean through galactic walls like cosmic artillery. What makes these temperatures so mind-bending isn't just the numbers, it's how they warp reality itself. At 100 million degrees, even the concept of temperature starts to blur. Particles move so fast that Einstein's relativity becomes critical. Their mass increases, time dilates, and collisions produce not just light but matter-antimatter pairs. Active galactic nuclei don't just burn hot, they rewrite the rules of physics in their cores, proving once again that the universe's most extreme environments are also its most creative laboratories. Gamma-ray bursts are the universe's most violent farewells, cosmic explosions so intense they outshine entire galaxies for seconds, then leave behind an afterglow hotter than 1 billion degrees Celsius. These aren't just fleeting flashes, they're catastrophic signposts marking the collapse of massive stars into black holes or the mergers of neutron stars, events so energetic they warp spacetime itself. When NASA's Swift satellite detected GRB 080919c in 2008, the afterglow's X-ray emissions revealed temperatures rivaling the cores of supernova, but concentrated into jets narrower than a pencil beam. What makes these afterglows so astonishing isn't just their heat, it's what that heat creates. As the jet plows through interstellar gas at 99.9% light speed, it generates shockwaves that act like natural particle accelerators. Electrons surfing these shocks emit synchrotron radiation across the spectrum, from radio waves to gamma rays, while the surrounding plasma reaches energies that make the sun's core seem frigid. This superheated environment becomes a crucible for nucleosynthesis, where rapid neutron capture, the same process that forges gold in neutron-star collisions, unfolds in real time. Spectroscopic analysis of afterglows has even detected absorption lines hinting at freshly synthesized heavy elements, suggesting these bursts might be cosmic goldsmiths on a staggering scale. The link between gamma-ray bursts and precious metals isn't just theoretical. In 2017, the LIGO and Virgo observatories caught gravitational waves from colliding neutron stars, while telescopes simultaneously recorded GRB 170817a. Follow-up observations revealed signatures of strontium, gold, and platinum in the explosion's aftermath, proving these events are literal foundries for the universe's heaviest elements. Every gold ring or platinum necklace owes its existence to similar cataclysms, stellar violence, transformed into tangible beauty over billions of years. Yet gamma-ray bursts are more than element factories, they're probes of cosmic evolution. Their afterglows act like backlights, illuminating gas clouds billions of light years away. By studying how this light gets absorbed, astronomers can map the distribution of matter across the universe, tracing the growth of galaxies from the primordial darkness. Some bursts even originate from epochs when the universe was less than 1 billion years old, offering snapshots of the cosmos in its fiery infancy. The sheer improbability of these events adds to their mystique. A typical galaxy might host just one gamma-ray burst every 100,000 years, making each detection a precious window into physics at the extreme. Their afterglows, though fleeting, burn with a brilliance that transcends their brief existence, proof that even in the universe's coldest voids, heat can still rewrite the rules of reality. Solar prominences are nature's grandest magnetic sculptures, towering loops of plasma stretching hundreds of thousands of kilometers above the sun's surface, glowing at temperatures between 50,000 and 2 million degrees Celsius. These ethereal ribbons of ionized gas might look delicate, but they're anything but fragile. Suspended by the sun's chaotic magnetic field, they can persist for weeks, arcing gracefully through the corona like bridges of fire. The Solar Dynamics Observatory has captured these structures in stunning detail, revealing how they twist and snap like rubber bands stretched to their breaking point, only to reform in new, even more intricate configurations. What makes prominences so mesmerizing is their stark contrast with sunspots. The sun's cooler, darker blemishes where temperatures plummet to a mere 3,000 degrees Celsius. While sunspots form where magnetic fields suppress convection, trapping heat beneath the surface, prominences occur where those same fields burst outward, channeling plasma into looping rivers of superheated gas. It's a cosmic push and pull. Sunspots siphon energy inward while prominences fling it into space. The SDO's ultraviolet cameras show this dichotomy in vivid color, sunspots appearing as inky voids against the sun's golden disk, while prominences blaze in brilliant reds and purples at the solar limb, dancing at the edge of visibility. The real drama unfolds when these magnetic loops become unstable. Sometimes a prominence will collapse under its own weight, sending billions of tons of plasma crashing back to the sun's surface at hundreds of kilometers per second. Other times, the magnetic field lines snap and reconnect in a process called magnetic reconnection, launching the entire structure into space as a coronal mass ejection. These eruptions can dwarf planets, their shockwaves rippling through the solar wind and triggering geomagnetic storms when they reach Earth. Yet for all their violence, prominences have an almost artistic quality. Some take the shape of towering curtains, their plasma threads aligned like vertical stitches in a celestial tapestry. Others form helical coils, twisted by the sun's rotation into spirals that could wrap around Jupiter. The largest observed prominence, recorded in 1946, stretched over 800,000 kilometers, long enough to loop from Earth to the Moon and back with room to spare. Solar physicists study these structures not just for their beauty, but for what they reveal about stellar magnetism. The same processes that shape prominences govern space weather, influence planetary climates, and even dictate the habitability of distant star systems. Every twisted loop, every explosive release, is a clue to understanding how stars sculpt their surroundings, and how their fiery tantrums might one day shape our future among the stars. Io's Loki Patera isn't just a lava lake, it's a roiling, shape-shifting nightmare the size of Lake Ontario, where temperatures hit 1,600 degrees Celsius and the very ground beneath it heaves like a restless sleeper. This 200-kilometer-wide cauldron of molten rock acts less like a terrestrial volcano and more like a cosmic pressure valve, releasing the pent-up fury of a moon being relentlessly kneaded by Jupiter's gravity. Every 42 hours as Io completes its orbit, the gas giant's gravitational pull stretches the moon like taffy, compressing its crust upward by 100 meters, enough to lift a 30-story building in mere hours. The friction from this constant flexing melts Io's interior into a global magma ocean, fueling over 400 active volcanoes that paint the moon's surface in swirling sulfurous yellows and fiery reds. What makes Loki Patera unique isn't just its sheer scale, it's its eerie predictability. Unlike Earth's volcanoes, which erupt sporadically, this lava lake follows a near-clockwork cycle. Every 400 to 600 days, a wave of fresh magma surges across its crusted surface, cracking the cooler top layer like ice on a pond and revealing the incandescent melt beneath. Infrared telescopes have captured these outbreak events in stunning detail, showing thermal waves propagating at roughly a kilometer per day as the lake renews itself in a slow-motion tantrum. The process mirrors Earth's plate tectonics but compressed into a single hyperactive feature, a volcanic heartbeat driven by celestial forces rather than internal convection. Jupiter's role in this drama can't be overstated. Alongside its larger moons Europa and Ganymede, the gas giant subjects Io to a gravitational tug-of-war called orbital resonance. For every orbit Ganymede completes, Europa makes 2 and Io 4, creating rhythmic pulls that keep Io's orbit elliptical rather than circular. This eccentric path means Jupiter's gravitational grip varies constantly, flexing the moon's crust with enough force to generate 3,000 times more heat than Earth's radioactive core. The result, a world where volcanic plumes shoot 500 kilometers into space high enough to spray particles directly into Jupiter's magnetosphere, and lava flows stretch hundreds of kilometers across plains of frozen sulfur dioxide. The violence of Loki-Patera's eruptions rewrites the rules of planetary geology. On Earth, lava viscosity depends heavily on silica content, but Io's magma is likely ultramafic, rich in magnesium and iron, giving it the consistency of motor oil. This allows it to flow rapidly across vast distances, creating rivers of molten rock wider than the Nile. Some flows might even be superheated, reaching temperatures 200 degrees hotter than typical basalt due to the intense tidal energy pumping into them. When these lavas meet Io's surface, frost largely sulfur dioxide at -130 degrees Celsius, the resulting explosions hurl debris at supersonic speeds, painting the surrounding landscape in psychedelic streaks of red, yellow, and black. Yet for all its fury, Io's volcanic activity might hold clues to Earth's own distant past. Before our planet developed rigid tectonic plates, its surface could have resembled Io's, a global magma ocean punctuated by massive, short-lived hotspots. Studying this hyperactive moon lets scientists test models of how terrestrial planets transition from molten chaos to the relative stability we enjoy today. It's a glimpse into a time when Earth itself was a seething cauldron, its crust constantly recycled by forces far wilder than anything we experience now, proof that sometimes, to understand our own world, we need to explore ones where the fires never went out. Co-Rho T7b is a world where geology becomes weather, a scorching inferno where daytime temperatures hit 2,500 degrees Celsius, hot enough to vaporize rock into a thin, mineral-laced atmosphere. This isn't just extreme heat, it's a planetary alchemist's playground where mountains might literally evaporate under the relentless stare of its host star. Discovered in 2009, this exoplanet orbits so close to its sun that a year lasts just 20 hours, and its surface is likely a global ocean of molten lava, churning with tides strong enough to warp solid ground into towering molten cliffs. The real spectacle happens at the boundary between day and night. Co-Rho T7b's tidal locking means one hemisphere bakes eternally while the other freezes in darkness. On the day side, silicate rocks like basalt and granite don't just melt, they sublime directly from solid to gas, creating an eerie atmosphere rich in sodium, potassium, and silicon monoxide. Winds carry these vaporized minerals to the night side, where temperatures plummet by over 2,000 degrees, causing them to condense into microscopic rock clouds. Imagine standing on this world. The sky might shimmer with flecks of crystallized minerals, while snowflakes of solidified lava drift downward, only to vaporize again as they slide back into the daylight. But Co-Rho T7b isn't alone in its brutality. K2141b, another lava world, takes the nightmare further with its hypothesized lava rain. Here, the dayside's molten surface, heated to 3,000 degrees, evaporates into a thin atmosphere of rock vapor, whipped by supersonic winds toward the night side. But instead of gentle snow, the condensing minerals form droplets of liquid rock that plummet back to the surface in violent, fiery showers. Telescopes have detected signs of this cycle in the planet's light curve, with infrared data suggesting a mineral atmosphere constantly replenished by vaporizing and recondensing crust. What makes these worlds so fascinating isn't just their hellish conditions, it's how they stretch our understanding of planetary science. Earth's water cycle, with evaporation, clouds, and rain, finds a twisted mirror in these lava worlds' rock cycles. The same forces that shape temperate planets operate here, just with different materials and at temperatures that defy imagination. Studying them helps astronomers refine models of atmospheric chemistry, tidal forces, and even the early history of rocky planets like Earth, which may have gone through their own magma ocean phases before cooling into habitability. These exoplanets also tease the limits of what we consider a surface. On K2141b, the boundary between land and sky might be a blurry, ever-shifting zone where rock becomes gas and back again. Co-Rho T7b's crust could be riddled with fissures constantly spewing fresh lava, like a slow-motion version of Eo's volcanoes. They're reminders that the universe doesn't just cater to our Goldilocks ideals sometimes. It forges worlds where the very ground beneath your feet is a fleeting illusion, sculpted and erased by heat beyond comprehension. For all their violence, these lava worlds offer something precious, proof that planetary diversity knows no bounds. From their molten skies to their mineral storms, they challenge us to rethink everything we know about geology, weather, and the line between solid and gas. They're cosmic laboratories where the rules get rewritten and every new discovery peels back another layer of their fiery mysteries. Not all storms rage under blue skies. Some churn in perpetual darkness where clouds aren't made of water but of molten iron and scorching sand. Take WISE 0855, a brown dwarf so cold it barely qualifies as a failed star. Yet its atmosphere boils with tempests that would dwarf Jupiter's great red spot. With temperatures hovering around 1,700 degrees Celsius, this cosmic loner hosts hurricanes of liquid metal and mineral vapors, swirling in vicious cycles that last for decades. Unlike Jupiter's iconic storm, which is powered by atmospheric convection and rotates like a slow-motion carousel, WISE 0855's maelstroms are fueled by the brown dwarf's own internal heat leaking into a turbulent, metallic soup. Infrared telescopes reveal these storms as blotchy patches of brightness shifting across the brown dwarf's face, evidence of colossal weather systems rearranging its cloud decks. The clouds themselves are nothing like Earth's fluffy cumulus. They're likely condensed droplets of iron and silicate minerals suspended in an atmosphere thick with hydrogen and helium. When temperatures dip just enough, these vapors condense into molten droplets, creating storms that rain liquid metal instead of water. Imagine a thunderhead where lightning arcs not through water vapor but through charged iron mist, its bolts hotter than the surface of most stars. Comparing these tempests to Jupiter's great red spot is like pitting a bonfire against a volcano. Jupiter's mega storm, while twice the width of Earth, operates at a frosty negative 160 degrees Celsius, its ammonia ice crystals swirling in relatively sedate winds. WISE 0855 storms, by contrast, blast through the brown dwarf's atmosphere at speeds exceeding 2,000 kilometers per hour, fast enough to cross the continental United States in under 30 minutes. And while Jupiter's spot has persisted for at least 400 years, brown dwarf storms may be more transient, flaring up and dissipating as the object's internal heat slowly leaks into space. What makes these metallic hurricanes so fascinating isn't just their violence. It's what they reveal about the blurred line between planets and stars. Brown dwarfs occupy a twilight zone where atmospheric physics starts mimicking stellar behavior, with global weather patterns dictated as much by radiative heat as by convection. Studying them helps astronomers predict what conditions might exist on gas giants orbiting distant stars, worlds where the very concept of weather transcends anything in our solar system. Yet for all their fury, these storms are invisible to human eyes. WISE 0855 emits no visible light, its dim glow limited to the infrared spectrum. If you could stand on its hypothetical surface, the sky would likely be a murky haze of glowing metals, backlit by occasional lightning that illuminates rolling clouds of liquid rock. It's a reminder that the universe's most extreme weather doesn't need sunlight to thrive, just heat, gravity, and a dash of interstellar chaos. Neutron stars wear crusts like Earth does, except these are forged from a metallic lattice 100 trillion times stronger than steel, glowing white-hot at 1 million degrees Celsius. This isn't solid ground as we know it. It's a quantum mechanical prison where atomic nuclei squeeze together so tightly they form bizarre shapes physicists call nuclear pasta. Picture a landscape where mountains are just a few centimeters high but denser than Mount Everest, their peaks trembling under gravitational forces so intense they bend light. And when these crusts crack, which they do violently, the resulting starquakes release more energy in milliseconds than our sun emits in centuries. The most infamous example erupted on December 27, 2004, when magnetar SGR 1806-20 unleashed the Christmas burst, a gamma-ray flare so powerful it briefly outshone the full moon despite being 50,000 light-years away. This wasn't just a stellar tantrum, it was a catastrophic snap of the star's crust, like a tectonic plate fracturing under unimaginable stress. As the magnetar's twisted magnetic field lines suddenly recoiled, they accelerated electrons to near light speed, generating X-rays detectable across half the galaxy. The burst actually ionized Earth's upper atmosphere, disrupting radio communications and lighting up satellites like cosmic fireworks. What makes these starquakes so terrifying isn't just their power, it's their unpredictability. Unlike Earth's quakes, which follow tectonic plate movements, magnetar crusts fracture under the strain of magnetic fields strong enough to distort atomic structures. These fields, trillions of times more intense than Earth's, pull the crust like taffy until it shatters, releasing pent-up energy as X-ray flares. NASA's Fermi Gamma-Ray Space Telescope has recorded these events as rhythmic pulses, with some magnetars experiencing hundreds of microquakes daily, each one a tiny adjustment in the star's rigid crystalline shell. The Christmas burst offered scientists a rare clue about neutron star interiors. By analyzing the oscillations in its X-ray afterglow, researchers realized the crust had vibrated like a struck bell, revealing its density and thickness. These seismic waves suggested a crust roughly 1 kilometer deep, thin compared to the star's 12-kilometer radius, yet containing half a sun's worth of mass compressed into a lattice of iron nuclei. Some theories propose that deeper layers might host even stranger materials, like superconductors where electric currents flow without resistance, or superfluids where neutrons swirl with zero friction. Yet for all their violence, these quakes are also cosmic goldmines literally. The shockwaves from crust fractures might trigger rapid neutron capture, the process that forges heavy elements like gold and platinum. Every time a magnetar's surface shudders, it could be sprinkling the galaxy with precious metals destined for future planets, and perhaps even future jewelry. The universe's most extreme temperatures don't just destroy, they create, proving once again that chaos and beauty are two sides of the same stellar coin. At the precipice of a black hole's event horizon, light doesn't just vanish, it becomes trapped in a deadly ballet, circling endlessly in a region called the photon sphere. Here, gravity warps spacetime so severely that photons orbit like planets around a star, creating a ring of superheated plasma glowing at 10 billion degrees Celsius. This isn't just theoretical, it's the fiery halo captured in the Event Horizon Telescope's groundbreaking image of M87, where scorching gas spirals into the abyss, illuminating the black hole's silhouette against the cosmos. The physics behind this phenomenon is as beautiful as it is violent. Light normally travels in straight lines, but near a black hole, spacetime curves so drastically that photons follow curved paths, some looping multiple times before either escaping to our telescopes or plunging into oblivion. The photon sphere marks the point of no return for these trapped rays, a boundary where gravity's grip is so precise that light orbits in perfect circles. Matter falling toward the black hole doesn't just vanish quietly. It piles up in this region, compressed and heated by friction until electrons are ripped from atoms, forming a swirling maelstrom of ionized gas. The result, a ring of plasma so energetic it outshines entire galaxies, its glow polarized by magnetic fields strong enough to twist the fabric of reality itself. M87's iconic image, released in 2019, revealed this structure in stunning detail. The bright crescent in the photo isn't the black hole itself, it's the photon sphere's ferocious glow, with light bent into a circle by gravitational lensing. The darker center, that's the shadow of the event horizon, a region where not even light can escape. What makes this image even more remarkable is its scale. The photon sphere spans a diameter larger than our entire solar system, yet it's so far away that capturing it required a virtual telescope the size of Earth, assembled from observatories across the globe. But the photon sphere isn't just a cosmic light show. It's a laboratory for extreme physics. The plasma here reaches temperatures rivaling the early universe, offering clues about how matter behaves under conditions impossible to replicate on Earth. Simulations suggest magnetic fields in this region act like cosmic particle accelerators, slinging electrons to near-light speeds and generating jets that shoot thousands of light-years into space. These jets, seen erupting from M87's core, might owe their existence to energy siphoned from the photon sphere's chaotic dance. The sheer violence of this environment defies intuition. Gas orbits at relativistic speeds, colliding with itself so violently that it emits X-rays and gamma rays. Some photons manage to escape their orbital prison, carrying with them distorted signatures of the black hole's spin, a fingerprint astronomers use to measure these monsters' rotation. Others spiral inward, fueling the black hole's growth. It's a cosmic recycling plant where matter is shredded, heated, and repurposed on a scale that humbles even the most energetic supernova. What makes the photon sphere so mesmerizing isn't just its heat or its light. It's the way it bends the rules of physics into a spectacle that's both deadly and dazzling. It's a place where the universe's most destructive forces also become its most brilliant beacons, proving once again that darkness and light aren't opposites, they're partners in the cosmic dance. Somewhere above Earth right now, a single subatomic particle screams through the atmosphere with more energy than a major league fastball despite being smaller than an atom. These cosmic rays, often protons accelerated to nearly light speed by distant supernovas or black holes, carry energies so staggering that when they collide with air molecules, they briefly recreate temperatures not seen since the first microsecond of the Big Bang, 100 million trillion degrees Celsius. That's a 1 followed by 20 zeros, a heat so intense it makes the core of a supernova feel like a winter breeze. The most infamous of these events happened on October 15, 1991, when the University of Utah's Fly's Eye detector spotted what scientists dubbed the "oh my god" particle. This single proton hit the atmosphere with the kinetic energy of a brick dropped from waist height, all concentrated into a speck smaller than anyone can imagine. The collision unleashed a shower of secondary particles so energetic they confused physicists for years, challenging the limits of what we thought possible from natural particle acceleration. For a split second, the impact point reached temperatures where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces may have briefly merged back into a single, unified superforce, just as they did at the universe's birth. These ultra-high-energy cosmic rays don't just break records, they break physics. Their existence defies conventional theories about how particles can be accelerated. Even the most powerful supernovas shouldn't be able to give protons this much energy. Some theorists speculate they might originate from active galactic nuclei, where black holes with the mass of billions of suns slingshot particles across intergalactic space like cosmic railguns. Others propose more exotic sources, colliding galaxy clusters, decaying dark matter, or even defects in the fabric of space-time left over from the Big Bang. When these particles strike Earth's atmosphere, they trigger air showers, avalanches of particles cascading down toward the surface at near light speed. By the time they reach the ground, the original collision's energy has splintered into millions of secondary particles spreading across kilometers. Arrays like the Pierre Auger Observatory in Argentina map these showers using tanks of purified water, waiting for the telltale flash of Cherenkov radiation as particles zip through faster than light can travel in water. Each detection is a forensic snapshot of that initial, unimaginably violent encounter. What makes these events so mesmerizing isn't just their scale, it's their intimacy. Every minute, cosmic rays pass harmlessly through your body, remnants of stellar explosions that occurred light years away, but the rare, ultra-high-energy ones. They're like messages from the universe's most extreme environments, written in the language of relativistic particles. By studying them, we're not just probing the limits of physics, we're touching the same searing heat that birthed the cosmos itself, one particle at a time. Imagine stars that don't shine, cosmic phantoms woven from dark matter, lurking in the void with temperatures barely above absolute zero. These hypothetical dark stars aren't just faint or cold, they're fundamentally alien, powered not by nuclear fusion but by the slow annihilation of dark matter particles deep in their cores. Unlike the blazing infernos we call stars, these primordial relics could have formed in the early universe, growing to gargantuan sizes without ever igniting the nuclear fires that light up conventional stars. Some theories suggest they might still exist today, invisible to telescopes yet sculpting the cosmos through their gravity. The concept hinges on dark matter's elusive nature. If certain hypothetical particles like weakly interacting massive particles, or WIMP, can collide and annihilate, they'd release energy just slowly enough to heat a star's interior without triggering fusion. Picture a celestial body the size of our solar system, its core simmering at a frosty 0 degrees Celsius, warmed only by the occasional annihilation of dark matter particles. These stars wouldn't have radiant surfaces or solar flares. Instead, they'd glow feebly in the infrared, their heat drowned out by the cosmic microwave background. Their structure would defy everything we know about stellar physics, with no need for the delicate balance between gravity and radiation pressure that keeps ordinary stars stable. The James Webb Space Telescope might hold the key to finding them. By peering into the distant universe where light from the earliest epochs is only now reaching us, astronomers could spot the infrared signatures of dark stars masquerading as unusually massive, cool objects. Some candidates already lurk in the data, strange, extended blobs in ancient galaxy clusters that don't quite fit the profile of ordinary stars or galaxies. If confirmed, these could be the smoking guns of a parallel stellar evolution, one where dark matter, not hydrogen, calls the shots. What makes dark stars so tantalizing isn't just their existence, it's what they'd reveal about the universe's infancy. Forming just a few 100 million years after the Big Bang, they could have been the seeds for supermassive black holes, their cores collapsing directly into the monsters that now lurk in galactic centers. They might also explain some of the universe's missing mass, hiding in plain sight as ghostly giants too cold to see. The irony is poetic. The darkest objects in the cosmos could illuminate our understanding of dark matter itself. If these stars are real, they're not just cosmic oddities. They're living fossils from a time when the universe was young and the rules of star formation were anything but ordinary. The void of space isn't as empty as it seems. It crackles with quantum energy where particles flicker in and out of existence so fast they defy measurement. These quantum vacuum fluctuations create fleeting heat spikes that, mathematically at least, reach temperatures approaching infinity, if only for infinitesimal moments. Picture the fabric of spacetime as a bubbling cauldron where virtual particle pairs, matter and antimatter constantly emerge before annihilating each other in bursts of energy so brief they leave no trace. But near the event horizon of a black hole, this dance gets disrupted in a way that bleeds energy from the abyss itself, Hawking radiation. Here's how it works. Normally, virtual particles annihilate so quickly they don't violate the conservation of energy. But at the edge of a black hole, gravity's tidal forces can rip these pairs apart before they recombine. One particle falls into the black hole, while the other escapes as real radiation. The math suggests these escaping particles carry energy siphoned from the black hole's mass, causing it to slowly evaporate over eons. The kicker: the radiation's temperature is inversely proportional to the black hole's size. A stellar mass black hole emits feeble Hawking radiation at near absolute zero, but a microscopic one would glow white-hot, its final moments a burst of energy trillions of degrees Celsius, proof that even the coldest voids can ignite under quantum rules. Theoretical as it sounds, this process ties back to those infinite temperature spikes in the quantum foam. When virtual particles separate at the event horizon, the energy required to promote them from fleeting fluctuations to real particles comes from spacetime's curvature itself. Some models suggest these interactions momentarily concentrate energy densities so extreme they rival the Big Bang's first instance, creating Planck-scale fireballs that vanish before they can be observed. It's as if the universe has a hidden furnace stoked by gravity and quantum uncertainty, flickering in and out of existence too fast to leave fingerprints. Hawking's theory reshaped how we view black holes, not as eternal traps, but as dynamic objects with temperature and lifespan. Yet the deeper implication is wilder. If quantum fluctuations can birth radiation, could they also explain other cosmic mysteries? Some theorists speculate similar mechanisms might power dark energy or even the universe's expansion. Others propose laboratory experiments to mimic these effects using sonic black holes in superfluid helium, where sound waves replace gravity, creating artificial event horizons that emit acoustic Hawking radiation. The quantum vacuum's seething energy reminds us that nothing is a loaded term in physics. Empty space crackles with potential, a canvas where particles and heat appear and vanish like mirages. From these fleeting fluctuations to black holes glowing their last, the coldest depths of space are anything but inert. They're a stage for some of reality's most incendiary performances. At 5.5 trillion degrees Celsius, the relativistic heavy ion collider didn't just break records, it rewrote the rules of heat itself. In 2010, scientists at Brookhaven National Laboratory smashed gold nuclei together at 99.99% light speed, recreating temperatures not seen since the universe was a mere microsecond old. For less than a billionth of a trillionth of a second, ordinary matter dissolved into quark-gluon plasma, a primordial soup where protons and neutrons melted into their fundamental components. This wasn't just hotter than the core of a supernova, it was 100,000 times hotter, a thermal spike so intense that even the strong nuclear force, nature's ultimate glue, briefly lost its grip on reality. The experiment's brilliance lies in its precision. By tracking the debris from these collisions, researchers mapped how quarks and gluons, normally imprisoned inside atomic nuclei, flowed like a frictionless liquid. This perfect fluid behavior defied expectations, proving that even at temperatures rivaling the Big Bang, quantum mechanics dominates. The plasma's viscosity was so low it could theoretically swirl forever without losing energy, a property that might explain how the early universe expanded so uniformly. Yet for all its artificial ferocity, RIC achievement pales beside nature's most extreme heat engines. Magnetar eruptions, for instance, can locally spike to 100 trillion degrees, while the photon spheres of feeding black holes sustain plasmas at 10 billion degrees indefinitely. The key difference: cosmic heat sources operate on scales that dwarf human ingenuity. A single gamma ray burst channels more energy in seconds than our Sun will emit in its entire lifetime, and active galactic nuclei maintain temperatures that would vaporize a planet across interstellar distances. What makes RIC plasma so revolutionary isn't the raw temperature, it's the control. By tuning collision energies, scientists can explore how matter transitions between phases, offering clues about neutron star interiors and the universe's first moments. The same physics that governed quark-gluon plasma might one day explain why we live in a cosmos dominated by matter rather than antimatter. These experiments blur the line between recreation and revelation. While stars and black holes generate heat through brute force, RIC's delicate ballet of destruction peels back layers of reality we're only beginning to comprehend. It's a reminder that sometimes, to touch the universe's extremes, we don't need to look to the stars, just deep into the heart of an atom. The universe's ultimate fate might not be fire but ice, an unimaginably slow descent into darkness so complete that even the last stars flicker out, leaving nothing but a void hovering just above absolute zero. This isn't just cold, it's the heat death of the cosmos, a paradox where maximum entropy doesn't mean chaos, but stillness so profound it defies comprehension. Picture a future so distant that trillions of years have blurred into eternity, where black holes themselves have evaporated, and all that remains is a sparse sea of particles drifting farther apart with every passing eon. The temperature, -273.15 degrees Celsius almost, but never quite, reaching absolute zero. The physics behind this chilling destiny hinges on entropy, the universe's stubborn tendency toward disorder. Every star that burns, every galaxy that collides, every life form that metabolizes energy, all of it pushes the cosmos closer to a state where energy is evenly smeared across space like butter on toast, with no concentration left to do work or spark change. Even now, the cosmic microwave background, the fading afterglow of the Big Bang, cools by a fraction of a degree each million years as space expands, dragging the universe's baseline temperature ever downward. But here's the twist: absolute zero isn't just a temperature floor, it's a barrier the universe can never quite breach. Quantum mechanics ensures that even in the emptiest reaches of space, particles retain a faint jitter called zero-point energy, a whisper of motion that prevents perfect stillness. The cosmos might asymptotically approach this limit, cooling to within a billionth of a degree above it, but true absolute zero would require freezing out quantum fluctuations themselves, an impossibility baked into the fabric of reality. This glacial twilight won't arrive quietly. Long before the final freeze, galaxies will vanish over the horizon of an accelerating universe, their light stretched beyond detectability by dark energy's relentless push. Black holes, the last holdouts of concentrated energy, will leak away via Hawking radiation over Googol-year timescales, their dying glow the universe's last flicker of heat. Eventually, even protons, the building blocks of atoms, might decay, reducing all matter to a thin haze of electrons, neutrinos, and photons so redshifted they're effectively invisible. The irony is profound. A universe born in fire could die in cold so deep it makes Pluto's winters feel balmy. Yet this frigid end isn't oblivion, it's transformation. Energy still exists, but it's become useless, like a battery drained too evenly to power even a single spark. Time loses meaning when nothing changes. The universe becomes a static monument to its own past, frozen in a state that's neither alive nor dead, but simply finished. For all its bleakness, the heat-death scenario reveals something startling about existence. The universe's initial conditions, the precise balance of matter, energy, and expansion that allowed galaxies to form, were so finely tuned that its eventual cold demise was almost inevitable. Had the Big Bang unleashed even slightly more energy, everything might have ripped apart too soon. Slightly less, and gravity could have collapsed it all back into a singularity. Instead, we're left with a cosmos that burns bright just long enough for life to emerge and wonder at its own fleeting place in the story, a story that trillions of years from now will have no one left to read it. Before temperatures existed, before even the concept of heat made sense, there was the Planck epoch, a sliver of time so brief it defies human intuition. This was the universe's first 10 to the negative 43 seconds, a period where the cosmos was smaller than an atom, denser than a neutron star, and so incomprehensibly hot that our current laws of physics simply dissolve into chaos. At these scales, energy and gravity were so tightly intertwined that particles as we know them couldn't form. There was no hot or cold, as just a seething quantum foam where space-time itself flickered in and out of existence like static on a broken screen. What makes this era so baffling isn't just the extreme conditions, but the fact that our understanding of physics hits a wall. Einstein's general relativity, which beautifully describes gravity on cosmic scales, clashes violently with quantum mechanics, the rules governing the subatomic realm. In the Planck epoch, gravity wasn't just a force, it was a fluctuating, foamy mess at scales where space and time lost their smooth continuity. Theorists call this the quantum gravity problem, and solving it might require a theory so radical it rewrites our conception of reality itself. Some candidates, like string theory or loop quantum gravity, suggest space-time could be pixelated at this level, built from indivisible units far smaller than atoms. Others propose extra dimensions curled into invisibility, or even a holographic universe where our 3D reality is just a projection of deeper, two-dimensional information. One thing's certain, the Planck epoch was a realm of pure potential. Without stable particles or even a clear arrow of time, the universe existed in a state where every possible configuration might have flickered into being simultaneously. It's like trying to describe the moment before a light switch flips. Was the room dark, if darkness as we know it hadn't been defined yet? This epoch ended when the universe expanded enough for gravity to split from the other fundamental forces, setting the stage for particles, and with them the first meaningful temperatures to emerge. The lingering mystery of this era isn't just academic. If we could peer into the Planck epoch, we might uncover why our universe has the precise balance of forces that allow stars, planets, and life to exist. Was this balance inevitable or the result of some deeper, unseen mechanism? For now, the Planck epoch remains the ultimate cosmic cliffhanger, a chapter written in a language we're still learning to decipher, hinting at truths that could redefine everything we know about existence itself. Tardigrades, microscopic creatures no larger than a grain of sand, defy every rule we thought we knew about survival. These eight-legged extremophiles, affectionately nicknamed water bears, thrive in conditions that would obliterate most life, scorching volcanic vents at 150 degrees Celsius, the crushing depths of the ocean floor, even the vacuum of space. But their most astonishing feat, enduring temperatures just 1 degree above absolute zero, a hair's breadth from the coldest possible state of matter. These creatures don't just tolerate extremes, they embrace them, entering a state called cryptobiosis where they dehydrate their bodies almost entirely, replacing water with a sugar that acts like molecular antifreeze. Their DNA shatters under radiation, only to stitch itself back together like a self-repairing zipper. What makes tardigrades so revolutionary isn't just their toughness, it's what they imply about life's potential beyond Earth. If organisms on our planet can withstand conditions mimicking the surface of Mars or the icy moons of Jupiter, why couldn't similar life exist out there? Consider Europa, Jupiter's frozen moon, where an ocean twice the volume of Earth's lurks beneath an ice shell, or Enceladus, spewing geysers of water vapor into space from its subsurface sea. These aren't just sterile wastelands, they're potential havens for extremophiles, worlds where tidal forces and chemical reactions could sustain ecosystems entirely alien to our sun-drenched experience. Scientists have even recreated extraterrestrial conditions in labs to test these theories. In 2017, researchers exposed tardigrades to the simulated atmosphere of exoplanet TRAPPIST-1e, a world orbiting a red dwarf star, and the creatures not only survived but later revived and reproduced. This experiment shattered the long-held assumption that life requires Earth-like conditions, suggesting that habitable zones might be far broader than we imagined. A planet tidally locked to its star, with one side perpetually scorched and the other frozen, could still harbor life in the twilight between. The implications are staggering. If tardigrades can persist in the void of space or the pressure cooker depths of Earth's hydrothermal vents, life might be hiding in the unlikeliest corners of the cosmos, perhaps in the methane lakes of Titan, the sulfuric acid clouds of Venus, or even the subsurface aquifers of arid Mars. Every new extremophile discovered on Earth expands the menu of possible extraterrestrial habitats, forcing us to rethink the very definition of livable. Yet tardigrades are just one piece of the puzzle. Other extremophiles, like the radiation-loving Deinococcus radiodurans or the acid-resistant ferroplasma, push the boundaries further. These organisms don't just survive hostile environments. They metabolize, reproduce, and evolve there, proving that life isn't a fluke of ideal conditions but a tenacious force that sculpts itself to the universe's harshest contours. As we search for life beyond Earth, we're not just hunting for pale blue dots, we're seeking the shadow biospheres, the outliers thriving where no one thought to look. The lesson of the tardigrade is clear. Life, once it takes hold, refuses to be confined by our narrow expectations. Across the universe, in boiling geysers and glacial deserts, creatures we've yet to imagine might be waiting, proof that the cosmos is far more inventive and far more habitable than we ever dared to dream. Temperature isn't just a number, it's the universe's unseen architect, shaping everything from the birth of stars to the sprawling web of galaxies. Picture a cloud of gas floating in the void, so cold it barely moves. Then a ripple, perhaps from a nearby supernova, compresses it just enough for gravity to take over. As atoms pack tighter, friction ignites a spark of heat, triggering a cascade where collapsing gas transforms into a protostar. This delicate dance between heat and gravity isn't unique to stellar nurseries. It's the same force that sculpts galaxies, drives weather on planets, and even dictates the chemistry of life itself. Take spiral galaxies like our Milky Way. Their elegant arms aren't static, they're waves of density where slightly warmer gas and dust clump together, pulled by gravity's tide. These regions become stellar factories, their higher temperatures resisting collapse long enough to birth star clusters. Meanwhile, in galaxy clusters, the universe's largest structures, hot gas between galaxies acts like a cosmic glue, its million-degree plasma emitting X-rays that reveal the gravitational scaffolding of dark matter. Without these thermal gradients, the universe would be a featureless sea of particles, devoid of the structures that make it dynamic. Even on smaller scales, temperature rules. Inside planets, heat from radioactive decay and primordial collisions churns molten cores, generating magnetic fields that shield atmospheres from solar winds. On icy moons like Enceladus, gentle warmth from tidal flexing maintains subsurface oceans, creating niches where life could cling. And in the emptiness between stars, microscopic variations in the cosmic microwave background, the faint afterglow of the Big Bang, trace the seeds of all future structure, imprinted when the universe was a seething plasma. The irony is profound. The cosmos thrives on imbalance. Absolute cold brings stagnation, while uniform heat leads to chaos. It's the in between the pockets of difference, the cliffs and valleys of temperature, that power creation. From quark-gluon plasmas to the slow fade of white dwarfs, heat isn't just a property of matter. It's the currency of change, the language in which the universe writes its story. And every time a star ignites or a galaxy spins, it's proof that equilibrium isn't the end. It's the silence between the notes. Humanity's quest to push temperature extremes isn't slowing down. it's accelerating, with missions and experiments poised to rewrite the record books. The European Space Agency's JUICE spacecraft, launched in 2023, is barreling toward Jupiter's icy moons with one audacious goal: to probe the frigid oceans beneath Ganymede's frozen crust, where temperatures hover near -200 degrees Celsius. But here's the twist: this isn't just about measuring cold. By studying how tidal forces from Jupiter's gravity flex these moons, scientists hope to calculate the precise heat needed to maintain liquid water under ice shells dozens of kilometers thick. It's a cosmic balancing act where a few degrees too much or too little could mean the difference between a lifeless ice ball and a hidden aquatic sanctuary. Meanwhile, back on Earth, the ITER fusion reactor in France is chasing the opposite extreme, recreating the 150 million degree inferno that powers stars. Unlike previous tokamaks that sustained fusion for mere seconds, ITER colossal magnets and plasma chambers aim to achieve a tenfold energy gain, maintaining stellar temperatures for minutes at a time. The secret lies in its superconducting coils, chilled to -269 degrees Celsius, just 4 degrees above absolute zero, to create magnetic fields strong enough to bottle a sun's worth of heat without melting the reactor itself. This marriage of extreme cold and extreme heat could unlock limitless clean energy, mimicking the processes that light the cosmos. But the real game changers might be the unassuming probes venturing into overlooked corners of the solar system. NASA's Dragonfly mission, set to land on Titan in the 2034, will navigate moon-wide methane lakes at -180 degrees Celsius, its rotors slicing through an atmosphere 4 times denser than Earth. Unlike Mars rovers limited by solar power, Dragonfly's nuclear battery thrives in the cold, turning Titan's cryogenic environment into an advantage. Meanwhile, astrophysicists are developing quantum sensors capable of detecting temperature fluctuations from the earliest moments of the universe, variations as minuscule as a millionth of a degree, imprinted when spacetime was barely a second old. The future of temperature extremes isn't just about breaking records, it's about decoding the universe's hidden language. From the quantum vibrations of supercooled atoms to the plasma storms of distant stars, every degree tells a story. And as our tools grow sharper, we're not just observers anymore, we're becoming conductors of cosmic heat, learning to play the universe's thermal symphony, one groundbreaking experiment at a time. From the Boomerang Nebula's whisper-thin chill near absolute zero to supernovas blasting matter at trillions of degrees, the universe thrives on thermal extremes that defy imagination. These aren't just numbers, they're the invisible hands sculpting galaxies, forging elements, and even dictating whether life can flicker into existence. Think of temperature as the universe's grand conductor, orchestrating everything from the slow death of white dwarfs to the quantum storms raging inside neutron stars. Without these dizzying contrasts, planets wouldn't coalesce, molecules couldn't bond, and the cosmic web would remain a formless void. Consider how much hinges on a single degree. If the sun's core were slightly cooler, fusion would sputter out like a damp match. If Earth's atmosphere trapped just a fraction more heat, we'd mirror Venus's scorching hellscape. Even the frigid gaps between stars play their part. Those near-perfect vacuums let radiation travel untouched for eons, carrying whispers of the Big Bang itself. From the trillion-degree quark soup of the early universe to the eventual heat death where all energy disperses into silence, temperature isn't just a measurement. It's the universe's autobiography, written in gradients of fire and frost. And the wildest part, we've only scratched the surface. What undiscovered extremes lurk in the hearts of rogue planets, or in the jets of supermassive black holes we've yet to image? Could there be materials that defy our laws of thermodynamics, lurking in the magnetic fury of undiscovered magnetars? The cosmos loves to surprise us, after all. Who'd have predicted a moon like Io, where lava lakes simmer beside sulfur frost, or a star like Kelt 9b, where the sky rains molten metal? So here's your invitation. Imagine what's next. Maybe you're fascinated by the icy frontiers of Europa's hidden ocean, or the way dark matter's phantom chill might shape galaxies. Whatever sets your curiosity ablaze, the universe has a thermal tale to tell. Drop your favorite fact below. Was it the neutron star's diamond crust or the mind-bending heat of the Planck epoch? And if you're hungry for more cosmic wonders, hit subscribe. The universe isn't done turning up the heat or dialing it down to bone-chilling new lows. The next extreme, it's out there, waiting to rewrite the rules.